Hello my dear students, welcome to IMS GATE Academy. Myself Prateek Mishra, mentor for civil engineering at IMS GATE Academy. Hopefully your preparation is going good for GATE examination. You have given your 8 months and you have shown real dedication towards this GATE examination. So for this very last moment of time when we are just 10 days away from GATE examination, revising all your concepts, all your formulas plays a very key role in deciding how your examination will go on upcoming 5th of February and on 12th of February, right? So we will going to start with the quick revision session for environmental engineering. I hope you have seen our GATE Booster series and you have also practiced the question and concepts that we have discussed in our GATE Booster series. You can go back to our channel, check with the playlist there, and you can go to the environmental engineering session for GATE Booster series, okay? There we have discussed expected questions, important concepts regarding environmental engineering. I have already told you that environmental engineering is one of the highest weighted subject for GATE examination when we talk about civil engineering. Entire environmental engineering covers around 10 to 15 marks in GATE examination. Environmental engineering is divided into wastewater engineering, raw water engineering, solid waste management and air pollution. This is the entire syllabus of environmental engineering, and the weightage of environmental engineering is 10 to 15 marks, right? And 10 to 15 marks plays a key role in getting you a very good rank. When we talk about getting a good rank, my dear students, you should focus on two important aspects. First, how you are reading the question. Because if you have read the question properly, your half of the solution is done, right? But if you are not reading the question properly, your answer may not be there. Aditya is saying, what about noise pollution, sir? Aditya, noise pollution is not there for civil engineering, but noise pollution syllabus is there when you attempt environmental science and engineering separate exam, right? From civil engineering, you can appear in two examinations. One is for core civil engineering and there are other optional subjects as well, right? You can appear for environmental science and engineering, you can appear for geomatics, you can appear for other exams as well, right? So there noise pollution is there, but when we focus on civil engineering, noise pollution is not there in environmental science and engineering syllabus, right? When we talk about environmental engineering, it starts with raw water engineering. In raw water engineering, we learn about how the water is supplied to the community, right? So, in order to supply water to the community, we need to know how much amount of water to be supplied in the community. So, the first topic of discussion comes to be water demand, in which we calculate the total amount of water that is required in the community. Once we calculate the total amount of water that is required in the community, we need to know the population of the community. In order to calculate the total water demand, we need to know the population of the community. Let me check your question again. Aditya is saying again, I think noise pollution is excluded because it is used to be in the syllabus before. Yes, it was there in the syllabus before. But from past few years, noise pollution has been excluded from the syllabus of environmental engineering, right? So my audio video is clear to you? Voice is audible to you? Voice is audible? It is properly audible, right? Video is also clear to you? Okay. So I was talking about raw water engineering, in which we treat the water and supply it to the community for different usages. So first topic of discussion is water demand, where we calculate the total amount of water that is required in the community. In order to calculate the total amount of water required in the community, we need to know the population of the community. So the second topic comes out to be population forecasting, right? Once we know the population at the design period, then we can easily calculate the total amount of water that is required in the community. Once we have calculated the total amount of water that is required in the community, we need to identify different sources from where we can fetch this water, right? So the next topic of discussion comes to be sources of water. From the sources of water, once we have fetched the water, we need to analyze this water. So the next topic of discussion comes to be water quality parameters. Using water quality parameters, we analyze the existing quality of the water. Now, depending upon the existing quality of the water and the desired quality of the treated water, we decide what is the degree of treatment given to this water. So, the next topic of discussion comes to be treatment of water after water quality parameters. Once this water is treated in the water treatment plant, this water is stored in a unit which is known as service reservoirs. We see these overhead tanks in the community. These are one of the examples of service reservoirs, right? So, this treated water from the water treatment plant is stored in service reservoirs. So, the next topic of discussion comes out to be service reservoir. Once this water is stored in the service reservoir, it is distributed in the system or it is distributed in the community by the use of water distribution system. So, the last topic of discussion in our raw water engineering is water distribution system. So, in the entire raw water engineering, we talk about calculating the quantity of water required in the community. Then we identify different sources. Then after identify different sources, we fetch this water and we check the quality of this water using water quality parameters. Once we know the existing quality of the water and the desired quality of the treated water, we give the degree of treatment to the water, right? We give treatment to this water. And last, we store this water in service reservoir and we finally distribute using water distribution system. Once this entire water is there in the community, it is used up, this water converts into wastewater. So, the entire engineering of collecting this wastewater, transporting this wastewater to the sewage treatment plant, then treating this sewage and finally disposing of that sewage to different sources is termed as wastewater engineering, right? Then we have solid waste management, where we characterize or analyze the quality of solid waste, and then we have different treatment techniques of treating this solid waste, right? We also discuss about different type of transfer station and what is the utility of transfer station in the total management system of solid waste management. Last, we have air pollution, and in air pollution, we focus on different types of pollutants. Then we focus on calculating the air quality index. Then we focus on calculating the different types of plume or identify different types of plume depending upon the existing environment, how different types of plumes are formed. And then there is a unit conversion question that is usually asked in your GATE examination. So let us begin with raw water engineering, right? So the first topic of discussion is water demand. So the total demand of water that is required in the community comprises of domestic demand, industrial demand, institutional demand, water for public use, fire demand and thefts and losses. As the name says, domestic demand, it is the amount of water required for day-to-day purpose. Industrial demand corresponds to the amount of water required for industrial use. Institutional demand is the amount of water required for different institutes in the community. These institutes may be government offices, it may be high courts, it may be schools, hospitals. So all these institutes which are present in the community, the amount of water required is termed as institutional demand. Next, we have water for public use. So the amount of water that is required for road cleaning purposes, for gardening these public gardens, all that water comprises under water for public use. Then we have fire demand, right? So whenever any fire outbreak happens in the community, in order to firefight that fire outbreak, the amount of water required termed as the fire demand of water. Then we have thefts and losses. So during distribution of this wastewater, if there are any illegal connections in the distribution system or if there are any leakages in the distribution system, in order to account for that water, it comes under thefts and losses. When you add all these types of demand, you get the total demand in the range of 250 to 350 liters per capita per day. So this is the total amount of water. Good evening, Jagdish. Good evening. This is the total amount of water required, right? When we talk about fire demand, so fire demand, either it can be taken as one LPCD or it can be calculated using different empirical formulas. One thing you should keep a check on, whenever you are using any empirical formula, you need to keep a check on the units in which the parameter has to be substituted. And what is the final answer and in which unit we are getting the final answer from an empirical relation, right? So for calculating fire demand, we have all these empirical formulas starting from Government of India manual formula. Fire demand is equals to 100 root P. Here P is the population in thousands. So if the population of the community is given as 1 lakh, if the population of the community is given as 1 lakh, if the population of the community is given as 1 lakh, here the P has to be substituted as 100, because 1 lakh is 100 thousands, right? And the fire demand you will get using Government of India manual formula is in kiloliters. That is, we get the volume of the fire demand. Next is the Kachling's formula. According to Kachling's formula, fire demand Q is equals to 3182 root P. Here again P is the population of the community in thousands, and the fire demand we get in terms of discharge, and unit is in liters per minute, right? Next we have Freeman's formula. According to Freeman's formula, Q is equals to 1136 P by 10 plus 10. Again P is the population of the community in thousands, and here again we'll get the fire demand in terms of discharge, that is in liters per minute. You need to keep a check on all these units, because you might be applying the correct formula, but if you are not using the correct unit, the answer you will get will be still wrong, right? So you need to keep a check. Good evening all. Good evening Shashi sir. Good evening. Next is the National Board of Fire Underwriters method. If the population of the community is less than 2 lakh, then the fire demand Q is equals to 4637 root P into 1 minus 0.01 root P. Here also P is the population of the community in thousands, and here also we'll get the fire demand in terms of discharge, and the unit again is in liters per minute. If the population of the community is more than 2 lakh, then fire demand Q is equals to 5400 liters per minute for first fire, and it is equal to 9100 to 36400 for second fire. Last one is the Buston's formula. According to that, fire demand Q is equals to 5663 under root P. Here also P is the population of the community in thousands, and the discharge of fire demand that we get is again in liters, right? Liters per minute. So you can use all these empirical relations to calculate the fire demand. One thing I would like to tell you, with respect to GATE examination and only respect to GATE examination, you need not to assume anything from your side, right? If a question is there with respect to fire demand, then strictly it will be mentioned that out of all these relations, which relation you have to use. So the relation that is mentioned in the question, you need to apply that relation only. And in GATE examination, you need not to assume anything from your side. It is a graduate aptitude test for engineering. It checks your technical aptitude, right? It checks your technical aptitude. So please keep a check on that. Next we have various factors which are affecting the fire demand. So the first factor that affects the fire demand is the type of sewerage system. So as the name says, if your sewerage system is inefficient, right, you will require more water for domestic purposes. So type of sewerage system directly affects the domestic demand of water. Next is the extent of industrialization. For extent of industrialization, if your community has more industry, then what will happen that your industrial demand will be more. It is simple. If your community has more industry, then your industrial demand will be more. Hence, more will be your total demand of water. Next is your size of the city. If size of the city is more, then length of the road networks will be more. The size of the public gardens will be more. There, the amount of water required for these road cleaning purposes, for gardening these public gardens will be more. So, if size of the city will be more, your water for public use will be more, right? And that's how it affects the total demand of water. Next, we have type of gentry. If a gentry is high class, it is generally assumed that the amount of water required for domestic purposes will be more, hence more will be your total demand, right? So if your class of gentry is high, your domestic demand will be more, hence more will be your total demand. Next is your climatic condition. If your climatic conditions are hotter, then again your domestic demand will be more, hence more will be your total demand of water. Next is cost of water and quality of water, right? These two parameters indirectly affects the water demand. Cost of water and quality of water will going to affect the consumption of water, not the demand of water, right? You can take an example like that. If you are feeling thirsty and you want to consume 1 glass of water, that is the demand, right? That is the minimum amount of water required to remove your thirst, right? But what happens is, instead of 1 glass, you consume 3 glasses of water, right? So this 1 is your demand, this 1 is your demand, and this 3 is your consumption. So this is the basic difference between demand and consumption, okay? So this cost of water and the quality of water indirectly affects the water demand. It does not affect the demand of water, it affects the consumption of water, okay? Next, we have the pressure in the water distribution system. So if the pressure in the water distribution system will be more, then more will be the losses, hence more will be your total demand of water. So these are the different factors which are affecting the water demand. You need to keep a check which factor is affecting which demand, right? When we talk about GATE, we have 3 variety of question: multiple choice questions, and then we have multiple choice question. For multiple choice question, only one option is correct. Then we have multiple select question. For this multiple select question, more than one options can be correct. And these multiple select questions are usually statement based questions, right? So a lot of statements can be framed using environmental engineering. So I will focus and I'll keep a check that all the possibilities of the formation of the multiple select question can be covered in this session. Last, we have the numerical answer type question, in which you need to solve the numerical, and whatever answer you are getting, you have to enter it in terms of value, right? So GATE is a computer based test in which you need to enter the value of the final calculation that you done. So these are the 3 varieties of questions that are asked in environmental engineering. There's a huge possibility of the formations of all the 3 varieties of questions, okay? So these are the different factors that are affecting the water demand. Next, when we talk about the percentage ratio of maximum demand to the average demand, it can be calculated using Goodrich's equation, and according to that, percentage ratio of maximum demand to the average demand into 100 is equals to 180 into T raised to the power minus 0.1. So using this Goodrich's equation, you can calculate the fluctuation in the water demand. So the fluctuation in the water demand, for hourly demand it is 2.7, for daily demand it is 1.8, for weekly demand it is 1.48, for monthly demand it is 1.28, and for yearly demand it is 100. When I talk about fluctuation in the water demand, what I am saying is, just wait, if my fluctuation for hourly demand, is 2.7, it means that my maximum hourly demand is equals to 2.7 times of average hourly demand, is equals to 2.7 times of average hourly demand. So this is how you can use all the fluctuations, right? You can use all these fluctuations, and all these fluctuations are calculated using Goodrich's equation only. So using this Goodrich's equation, we get the percentage. These fluctuations are written in decimals, so you have to convert this percentage into decimals, right? The only limitation with this Goodrich's equation is, here the time you need to substitute, this time has to be more greater than or equal to 1 day, right? Here time has to be substituted in days, and the value of t has to be greater than or equal to 1 day. So using this Goodrich's equation, we cannot calculate the fluctuation in the hourly demand. Okay, moving on with this. Next is, once we know all the fluctuation in the water demand, right? Once we know all the fluctuation in the water demand, let me also talk about the design discharges. Let me also talk about the design discharges. So design discharges. Design discharges and design period. Design discharges and design life for the different equipments or the different parts of raw water scheme, right? So first one is the source. I'll just write down this. So source of water, first one is the source of water. Design discharge is maximum daily demand. Maximum daily demand is your design discharge, and design life is 50 years. Right. Then we have pipe 1. Which carries water from the source till the water treatment plant. The design discharge is again maximum daily demand, and your design life is 30 years. Your design life is 30 years. Next we have pumps. For pumps, again your design discharge is maximum daily demand, and your design life is 15 years. Next we have the water treatment plant. So for water treatment plant, my design discharge is maximum daily demand, and design life is 30 years. Sorry, this is 15 years. Design life is 15 years. Design life is 15 years. Next, we have the service reservoir. Service reservoirs are designed for fire demand plus emergency storage plus balancing storage. So this is the total quantity that is required from service reservoir. Design life is again 30 years. Next we have the distribution system. For the distribution system, design discharge is maximum of maximum hourly demand or coincident demand. Coincident demand is the sum of maximum daily demand plus fire demand. Coincident demand is the sum of maximum daily demand and the fire demand. I'll just check this. This is also 15 years. For service reservoir, the design life is 15 years. Right? So these are all the design discharges and the design life for the entire raw water scheme. Next, if in order to calculate the demand of water, we need to analyze or forecast the population of the community, right? So we have different methods of population forecasting. First method of population forecasting is arithmetic increase method, where the average increase in population is calculated, that is x bar, and we can forecast the population after n number of decades. So Pn is equals to P naught plus nx bar, right? Then using geometric increase method, we calculate the average percentage increase in population, that is R, and using this we can calculate or forecast the population after n number of decades using the relation Pn is equals to P naught into 1 plus R raised to the power n, where n is the number of decades from the base population. Base population is P naught. So from the year of P naught, how many decades away we need to forecast the population, correct? R is your percentage increase in population and n is the number of decades from P naught. Next method is your incremental increase method, where we calculate the average increase in population x bar, and then we calculate the increase over increase in population, that is the incremental increase in population, y bar. So using x bar and y bar, Pn can be calculated as P naught plus nx bar plus n into n plus 1 by 2 into y bar. So this is the relation for incremental increase method. The rate of growth of population of the community depends upon 4 factors. First one is the number of births that are happening place. Second is the number of deaths that are happening. Third one is the number of inward migration and the number of outward migration. These are the 4 factors which affects the growth of population in any community. We have one more method for forecasting the population, and this is also the graph based method, right? That is known as the logistic curve method. For logistic curve method, if we know population at time t naught is p naught, population at time t1 is p1 and population at time t2 is p2, then we can plot this curve and we can forecast the population after any time t. We can forecast the population after any time t. So, after any time t, population is p, right? And PS is the saturation population, that is the maximum amount of population that can reside in a community, right? So, using these simple relations, we can forecast the population. One thing we should keep a check before applying this logistic curve method, that your T2 should be equal to twice of T1. Then only you can apply this logistic curve method for forecasting the population. Using the relation natural log of PS minus P by P minus natural log of PS minus P naught by P naught is equals to minus K into PS into T. So, using this simple relation, you can forecast the population. This relation can also be written as P is equals to PS upon 1 plus M ln inverse NT, where M is equals to PS minus P naught. Is this okay? Is this okay to you? Is this okay to you? So, N is equals to, your N is equals to 1 upon T1, 1 upon T1 natural log of P1, sorry, P naught into PS minus P1 upon P1 into PS minus P naught. So, using this relation, you can forecast the population after any time t, right? So, this is all about the population forecasting and water demand. Right now, in GATE examination, you will find hardly any question from these topics, right? There are not many questions that are asked from water demand and population forecasting. But the next topic that we will going to discuss, it is a common topic for your geotechnical engineering, for your environmental engineering and also for your hydrology and irrigation, right? So, the next topic of discussion is the sources of water. Next topic of discussion is the sources of water. Sources of water. We know that water can be derived either from surface source, which can be any lake, it can be any river, and nowadays it can even be any sea or an ocean. It can be any sea or an ocean. Earlier, we do not treat this sea and ocean as the source of water. But now we can fetch water from sea and ocean and we can give sufficient amount of treatment to this water and we can use this water after treatment. Next, we have the subsurface sources of water. Next is the subsurface sources of water. Subsurface source of water, where we fetch this underground water, right? And for the subsurface of source of water, we usually depend upon the aquifers and springs. These are the two major sources of subsurface water, right? Whenever this water infiltrates and reaches the ground level, right? Reaches the groundwater level. When this water, this is my ground level, this is my ground level, and this is my groundwater table. This is my groundwater table, right? This is my groundwater table. So, whatever water which is penetrating through this ground, this water undergoes natural purification or natural filtration. So, this underground water is free from suspended solids. This underground water is free from suspended solids. This underground water is free from suspended solids. It does not contain suspended solids, underground water. So, whenever we are extracting this underground water, we need not to treat this water for suspended solids. For suspended solids, it is highly available, or suspended solids will be present in majority when we fetch water from any surface source, because this surface source of water is in direct exposure with the surroundings, and there are chances that all the suspended solids in the surroundings can get mixed in this surface source of water, right? Your surface source of water basically includes rivers, lakes, ponds, seas and ocean, and your subsurface water includes your aquifers and springs, right? When we talk about how or from where we need to fetch this underground water, so we need to study about where the water is exactly available, from where this water can be fetched, right? So next topic of discussion is your groundwater development. Groundwater development. In this, we study about at which particular layer of below the earth's surface water can be feasibly extracted, right? So when we talk about different layers that are present, so if this is my ground level, and if we go deep inside the ground level, this region below the ground level can be broadly classified into two zones. First one is known as the zone of rock fracture. This is known as the zone of rock fracture. I'll write here. This is known as the zone of rock fracture. And below this, we have the zone of rock flowage. Zone of rock flowage. This is zone of rock flowage. In the zone of rock flowage, water is present, or the water molecule is present inside the crystal structure of the medium particles. So in order to fetch this water, we need to break this lattice, and then we can fetch this water, right? And it is very clear that we will not going to give such efforts to fetch this water which is present inside the crystal structure, which is present, water is present inside crystal structure. Water is present inside crystal structure of the medium particle. So in order to fetch this water, we need to break the lattice of the medium particle, then only we can fetch this water. So this zone is of no engineering use when we talk about extraction of underground water, right? When we come above that, in the zone of rock fracture, this is divided into two major zones. So this is known as zone of saturation. This is zone of saturation. And this zone is marked by the presence of groundwater table. In this zone only, my groundwater table will be present, and the upper limit of this zone will be marked by the level of groundwater table, right? This is the zone where degree of saturation is 1, which is completely saturated, and only from this zone we can feasibly extract this underground water. Above this, we have a zone which is known as zone of aeration. So this is my zone of aeration. This is zone of aeration. And this zone is classified into 3 layers. This is sub-classified into 3 layers. So above zone of saturation, we have capillary water zone, capillary water zone, and in this capillary water zone, it is again 100% saturated through capillary action. But due to the extra surface tension force acting over this capillary water, we need to give extra effort to extract water from this capillary water zone. So again, this capillary water zone is not used for extracting this underground water, right? Above that, we have intermediate water zone. We have intermediate water zone, where degree of saturation is less than 1, and above that we have the root zone. We have the root zone. So these are the different zones in which the soil is classified below the ground level. This is my ground level. For root zone also, degree of saturation is less than or equal to 1. During irrigation or during rainy season, the degree of saturation for the root zone is 1, right? So only from zone of saturation we can extract this water. Now talking about what are the factors over which this groundwater extraction depends. So there are two factors over which the extraction of groundwater depends. First factor is known as the porosity of the soil medium. Porosity is the simple ratio of volume of voids to the total volume of the soil medium. If the medium has more porosity, it means it has more number of voids. It means more amount of water can be stored in that medium, right? So porosity tells us about the quantity of water that is stored in the medium. When we talk about the fine-grained soil and the coarse-grained soil, fine-grained soil has more porosity, right? It has more volume of total number of voids, okay? Next factor is the permeability. Permeability tells us how easily we can fetch this water. Permeability indirectly tells us what is the frictional force that is applied by the medium when we extract this groundwater. So if the medium is applying more frictional force, obviously we need to apply more effort to extract this underground water, okay? So if your medium is applying more frictional force, obviously your permeability will be less. Permeability is the ease with which water can flow through the interconnecting voids of the soil medium. So if more friction is there, lesser will be the permeability of the medium. So permeability is the rate of flow per unit area per unit hydraulic gradient. So K is nothing but K is equals to Q upon discharge per unit hydraulic gradient per unit area. K is equals to Q upon I into A. Some of the formulas that we derive using Darcy's equation. So average velocity of flow V is equals to K into I. Discharge Q is equals to K into I into A. Seepage velocity Vs is equals to your average velocity of flow divided by N, that is the porosity, multiplied by the degree of saturation. This seepage velocity is the actual velocity of flow through which the water will be flowing inside the medium, okay? One question is asked regarding the inner tracer, that in how much time if we apply the inner tracer at one well, it will going to reach the another well, right? So we will always consider this seepage velocity for calculating that time. Is this clear to you? Is this clear to you? Please tell me, is this clear to you? Okay. Moving on with this. If we take a situation where the water is flowing under the action of gravity, right? When the water is flowing under the action of gravity through the medium, when the water is flowing under the action of gravity through the medium, right? Not the entire water will going to flow out of the system. The amount of water which is flowing out of the system is denoted by a parameter which is known as specific yield. Specific yield, denoted by gamma S. And your specific yield is the ratio of volume of water drained divided by the total volume of medium drained. So gamma S is equals to Vd by V, where Vd is the total volume of water drained divided by the total volume of the medium. Then against the gravity, how much water is restricted or restrained is denoted by a factor which is known as specific retention, denoted by gamma R, and gamma R specific retention, which tells us that how much amount of water is retained against gravity or getting absorbed over the medium is gamma R is nothing but volume of water retained divided by the total volume of medium drained. Is this okay? Gamma R is equals to VR by V, where V is the total volume of water retained divided by the total volume of medium drained. Is this clear to you? Is this clear to you? Just 1 minute. So we have one more relation between gamma S plus gamma R. Gamma S plus gamma R is equals to porosity multiplied by degree of saturation. Mark it as one of the most important relation because using this relation, a lot of questions are framed in geotechnical engineering, in your environmental engineering, and also in your hydrology and irrigation. Okay. So this is the basic idea about how to calculate the amount of water that is draining out of the system and the amount of water which is retained against the action of gravity. And how this water is getting retained? This water is getting retained due to the absorption happening over the medium, right? If this is my soil medium like this, if this is my soil medium like this, then this soil medium will going to absorb some amount of water over its surface like this, right? So this is the water which is retained against gravity because this water is getting absorbed over the surface of the soil medium. Is this okay? Next, we have the different types of geological formations for depending upon the underground situation, right? So different types of geological formations include aquifers. So aquifers are both porous and permeable. Both porous and permeable, right? It means permeable. It means sufficient amount of water can be stored in the aquifers and also easily water can be extracted from these aquifers. Next we have aquicludes. Next we have aquicludes which are highly porous, but impermeable. But impermeable. These aquicludes are highly porous but impermeable. You can consider the example of a clay layer. Clay is a smallest type of medium that we are known to, right? If you talk about the increasing size of the medium, so sand is of more size. Above that we have gravel and other things. We have sand, then we have silt. And last we have clay, right? So this is the order of decreasing size. Sand is of more size, then we have silt and then we have clays, right? So aquiclude is both highly porous but impermeable. Then we have acutard. For acutard, it is porous but it is less permeable. Due to less permeability, for acutard, water seeps through the interconnecting voids. Water seeps through the interconnecting voids. And last we have aquefuge. This aquefuge is neither porous nor permeable. It is neither porous nor permeable, right? This is neither porous nor permeable. So if I want to arrange all these geological formations depending on the size of voids, right, or on the basis of porosity. So highly porous is acute, then we have acutard, then we have aquifer, and last we have aquifuge. So I'll write down. So increasing order of porosity is, or I should write decreasing order of porosity is, decreasing order of porosity is, first we have acute, first one we have acute, then we have acutard, then we have aquifer, and last we have aquifuge. This is the decreasing order of porosity. When we talk about the decreasing order of permeability, so the decreasing order of permeability, so highly permeable is aquifer. First one is aquifer, which is highly permeable. Aquifer is highly permeable. Then we have acutard, in which water is seeping through the interconnecting voids. We have acutard. So acutard is there. After acutard, we have aquinclude, which is almost impermeable. And last one is aquifuge. Last one is aquifuge, right? Last one is the aquifuge. You need to remember this decreasing order because a statement can be framed for a multiple select question, or even it can be asked for a multiple choice question also. So this is the decreasing order of porosity and permeability for all the types of geological formations. Okay. Now moving on with this, in order to extract this underground water. So the next topic of discussion is extraction of underground water. Extraction of underground water, extraction of underground water, extraction of underground water, extraction of underground water can be done through artificial construction, right? So the first artificial construction through which this underground water can be extracted is your infiltration wells. Infiltration wells. Infiltration wells. Then we have infiltration galleries. Then we have infiltration galleries. Then we have wells. Then we have wells. These wells can be of two types. First one is your open well. So first one is your open well. And next one is your tube wells. Next one is your tube wells, right? So through these artificial construction, we can extract this underground water. Starting with the infiltration wells, so what we do is, for infiltration wells, what we do is, if this is my river, if I'm drawing the plan of my river like this, so this is my plan of the river, right? So the water is flowing in this direction inside the river. So this is my plan. So in the banks of the river, we dig these infiltration wells like this. Along the bank of the river, we dig these infiltration wells like this. So these are the infiltration wells, right? If I'll just take the section of these wells, if I just take the section of these wells like this, if I consider this section XX and draw this, so this looks like something like this, right? So this is my well. I'll just draw in the another slide. So this is my cross section of the well. Right. So this is my infiltration well, right? This is the river water. This is my river water. This is my river water like this. This is my river water. This is the river water that is flowing. And from this river water, the water just seeps in towards the well and enters from the bottom. In the infiltration wells, water enter from the bottom. This water seeps into the well and it just enters from the bottom of the well, right? So these are my infiltration wells. So these are my infiltration wells that are dug along the bank of the river, right? These infiltration wells are dug along the bank of the river from where the water can be fetched from the bottom. Water can be taken from the bottom, right? And once this water is there for this infiltration well, it is collected in the main well, and this main well is known as the jack well. This main well is known as the jack well, right? So the water from these infiltration wells are transferred to these jack wells like this. This water is transferred to these jack wells like this, right? And from these jack wells, water is taken to the water treatment plant, right? Now, so this is the first artificial construction for extracting this underground water. Next is the next artificial construction that is used for extracting the underground water is termed as infiltration galleries. It is termed as infiltration galleries. Infiltration galleries are the long channels which are dug in 3 to 5 meter below the earth's surface. So I'll just draw the cross section. So if this is my ground level, and this is the water that is flowing in the river, right? So we will going to construct the infiltration galleries somewhere 3 to 5 meter below the surface of the ground level. We will construct this infiltration galleries 3 to 5 meter below the surface of the ground level. So this is the infiltration gallery. This is my infiltration gallery, right? This is my infiltration gallery. And from this river, the water will seep into this infiltration gallery like this. Water will seep in to the infiltration galleries like this, right? So this is the level of water that is there, right, in the infiltration gallery. If I'll take this as bottom, or datum, so the head of water at the river, this head is termed as H, capital H. The head of water inside the infiltration gallery is denoted by H naught. It is denoted by H naught. From the center of the infiltration gallery till the point from where water is coming to the infiltration gallery, this point, this is known as R, and R is known as the radius of influence. This R tells us that from which farthest distance the water is coming to the infiltration gallery, right? So these are the basics of infiltration gallery. This upper layer of water that is seeping to the infiltration gallery, this is known as the drawdown curve. This is known as the drawdown curve. This is known as the drawdown curve or Dupit's curve or sag curve or sag curve or sag curve, right? So if you consider all these parameters, right? If you consider all these parameters, there is an expression for calculating the discharge of an infiltration gallery. Is this okay? Is this okay to you? Please tell me. Is this okay to you? So the discharge through the infiltration gallery is equal to Q is equals to KL H square minus H naught square divided by 2R. Here H is the head of water at river. H naught is head of water inside infiltration gallery, inside infiltration gallery. Then we have R is the radius of influence, R is the radius of influence, radius of influence, and L is length of the infiltration gallery, L is the length of the infiltration gallery, and K is the permeability of the soil, K is the permeability of the soil, K is the permeability of the soil medium. K is the permeability of the soil medium, right? So using this, you can easily calculate the discharge through an infiltration gallery, right? Next artificial construction is the wells. Next artificial construction is the wells. Wells can be of two types, open well and tube well, and tube wells. These open wells are further of two types, shallow wells and deep wells. Shallow wells and deep wells. Now, don't go with the name. Thank you, Ankit sir. Thank you so much. Don't go with the names of these wells, right? Shallow well is not that well which is of less depth. Okay? Understand this. Shallow well and deep well are defined on the basis from where they are having the bottom support. If the well is not having the bottom support over the impermeable layer, it is defined as the shallow well. And if a well takes the bottom support from the impermeable layer, it is termed as the deep well. Is this okay? So shallow well and deep wells are defined on the basis from where they are having their ground support. Is this clear to you? Okay. Then we have tube wells. Tube wells are of two types. Tube wells are of two types. First type of tube well is known as your strainer type. First type of tube well is known as the strainer type. I am just wanting to tell you one thing. When we are discussing about these shallow wells and tube wells, right? When we are discussing about these shallow wells and tube wells, so I'll just draw this shallow well like this. So this is my shallow well which is not having any support from the bottom, right? This is not having any support from the bottom. This is my soil medium. This is my soil medium like this. It is not supported over the impermeable layer like this, right? So this is my soil medium from the shallow well. And if I draw a deep well, my deep well will look like this. So this is my deep well. This is my deep well. This is my ground level. This deep well will obtain a support from the lower impermeable layer like this. It will going to obtain support from the lower impermeable layer like this, right? And from this impermeable layer, this deep well will going to have support like this, okay? And below this, we have a layer like this. Both these open wells will going to derive water only from the bottom. Here, water is derived only from the bottom. From the sides, water is not derived from these open wells, okay? So if you have a well which is having the lower support of the impermeable layer, it is termed as a deep well. This is termed as a deep well. And if it is not having support of the lower impermeable layer, this is known as the shallow well, right? This is known as the shallow well. In order to increase the discharge from the shallow well, in order to increase the discharge of this shallow well, since area is constant, your velocity of flow will also going to increase. When we increase the discharge from the shallow well, your velocity of flow will also going to increase, and we should keep a check that this velocity of flow should not exceed the settling velocity of this medium particle. Because if this velocity of flow exceeds the settling velocity of the medium particle, then these medium particle will start flowing out of the medium. This medium particle will start flowing out along with the water, and what will happen is there will be destabilization of this wall lining. This phenomena due to which the particles start coming out of along with the flow is termed as piping. This is termed as piping. This is termed as piping, and if the piping happens in the shallow well, it will lead to the destabilization of the wall lining. Destabilization of well lining. Destabilization of well lining, right? So we need to keep a check that this discharge should not be exceeded to such a value that velocity of flow exceeds the critical velocity, that is the settling velocity of the medium particle. If such thing happens, then this particle will start coming along with the flow, which is termed as piping, and due to this piping, destabilization of the wall lining will going to happen, right? So this is one of the problem with shallow well, but for deep well, no such piping will going to affect the well lining, right? Because here the support is derived by this lower impermeable layer, and even if the particles starts coming out along with the flow, only thing that will happen is the formation of cavity at the bottom of these wells. So this is the cavity formation. This is the cavity formation. That is the only thing that will going to happen on increasing the discharge. But for shallow well, you will even see that this well may sink due to destabilization of the wall lining. Okay. So hopefully this is clear to you. This is clear to you. Next, moving on with this, I was talking about tube wells. So tube wells are of two types, strainer type or cavity type tube wells. Cavity type tube wells, right? Strainer type or cavity type tube wells. For cavity type tube wells, it will again going to derive water from the bottom. They will again going to derive water from the bottom. But for strainer type tube well, they will going to derive water from its surface. That is the curved surface of the well. From the curved surface of the well, these strainer type tube wells will going to derive their water. Let us see how they will going to do so. So, when I draw a cavity type tube well, so this is my cavity type tube well. So this is my cavity type tube well. For this cavity type tube well, this will only going to derive water from its bottom, right? It will only going to derive water from its bottom. The pipe is not porous, hence it is termed as blind pipe. It is termed as blind pipe. It is termed as blind pipe, right? Next, if I talk about screen type tube well, so for screen type tube well, I have this type of tube well like this. This is my tube well. This is my tube well. Okay. So this tube well will be closed from the bottom by the help of bail plug. So this is the bail plug through which this tube well will be closed from the bottom. So screen type tube well will be closed from the bottom, and first you have a gravel layer that is present around the walls of the well like this. You have this gravel layer which is present around the walls of the well like this, right? So this type of screen type tube well is known as the gravel pack type. It is known as the gravel pack type. It is known as the gravel pack type. And in these gravel pack type tube well, water will enter from the sides like this. Water will enter from the sides like this. So this is my gravel pack type tube well where the water is entering from the side. Okay, I have written here strainer type tube well, so you can correct it. It is screen type tube well. So this is screen type tube well, right? So this is screen type tube well. So this is screen type tube well. Screen type tube well are of two types, gravel pack type and second one is the strainer type tube well. So first type of screen type tube well is the gravel pack type. Next type of screen type tube well is known as the strainer type tube well. So for strainer type tube well, we have a tube well like this. Again, this strainer type tube well will be closed by the means of bail plug from the bottom. It will be closed by the means of bail plug from the bottom. It will be closed by the means of bail plug from the bottom, and we have screens that are present over these wells like this. We have these screens that are present over these wells like this. We have these screens that are present over these wells. These screens will going to restrict the medium particles from entering along with the flow. So for this screen type tube well also, water will be coming from the sides. And due to more depth of these type of tube wells, it will going to fetch more amount of water or the more quantity of water, right? So these are the two types of screen type tube well. First one is your gravel pack type and second one is your strainer type tube well. In gravel pack type tube well, again, this gravel layer is used to restrict the entry of the medium particles along with the flow. And also for the screen type tube well, this strainer type tube well, the screens are placed which will again going to restrict the entry of the medium particle along with the flow. Is this okay? Next is in order to calculate discharge from an open well, we have two methods. First one is the field test. And second one is the recuperation test. First one is the field test and second one is the recuperation test, right? So for field test, Q is equals to CAS and Q is the discharge corresponding to any drawdown S. A is the area of cross section of the shallow well and C is known as the specific yield. And this specific yield is calculated corresponding to a known discharge and a known drawdown. So C is equals to Q naught upon A into S naught, right? So this is the value of C, and using this constant value of C, we can calculate discharge corresponding to any drawdown S, right? For this recuperation test here, the value of C is natural log of S1 by S2 divided by T2 minus T1, right? So for recuperation test, C is calculated like this, and again using the same relation, Q is equals to CAS, we can calculate discharge corresponding to any drawdown S, but C has to be calculated like this. C is equals to natural log of S1 by S2 divided by T2 minus T1, right? So these are the results directly from the field test and the recuperation test. Next, when we want to calculate the discharge for a tube well, we have two methods. First one is your Dupit's theory. And second one is your Thiem's theory. Right? For tube well in an unconfined aquifer, according to Dupit's theory, your discharge Q is equals to pi k h square minus h naught square divided by natural log of capital R by RW. So this is the relation for calculating the discharge for a tube well in an unconfined aquifer using Dupit's theory. Using Thiem's theory, same discharge can be calculated as pi k h1 square minus h2 square divided by natural log of R1 by R2, right? So this H1 and H2 are the drawdown in the observation well number 1, the head at observation well number 1, and H2 is the head at observation well number 2. R1 is the distance of first observation well from the center of the main well, and R2 is the distance of second observation well from the center of the main well, right? So using these Thiem's theory and Dupit's theory, you can calculate the discharge for a tube well in an unconfined aquifer. For a tube well in confined aquifer, 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 using Dupit's theory, using Dupit's theory, your Q is equals to 2 pi kd capital H minus small h naught divided by natural log of capital R by small r. And according to Thiem's theory, this discharge can be calculated as, Q is equals to 2 pi kd H1 minus H2 divided by natural log of R1 by R2 So this is the calculation of discharge for a confined aquifer using Dupit's theory and Thiem's theory, okay? Here K is the permeability of the soil medium, D is the depth of the confining layer. So D is the depth of the confining layer. So if your aquifer, if you have well like this, I'll just draw. So this is my ground level, and in this ground level I have well like this. I have a tube well like this. This is my tube well. This is my first impermeable layer or the upper impermeable layer. And below this, I have another impermeable layer. So the distance between two impermeable layer is known as the depth of the confining medium, right? So this is my D. This is my D, right? And this tube well is extending inside this confining layer so that the water can enter from the side of these wells. Right? So this is the well in a confined aquifer, okay? Now one thing you should always take care that whenever the well is present between the two confining layer, some additional pressure is there which is known as the artesian pressure, right? And this artesian pressure is due to the revolution of the Earth's surface. So these are the total formulas that you need to take care when we talk about the sources of water. Once we have extracted this water, we need to analyze this water using water quality parameters, right? So the next topic of discussion is water quality parameters. Water quality parameters. In order to analyze the water, we will analyze using water quality parameters. These water quality parameters are of three types. First one is the physical water quality parameter. All the water quality parameter that can be felt or sensed by any of our senses is termed as physical water quality parameter. Next we have the chemical water quality parameter. So all the water quality parameter which affects the chemical quality of water comes under chemical water quality parameter. Third one is the biological water quality parameter. Biological water quality parameter. In biological water quality parameter, we basically focus on calculation of the number of pathogens present in the medium. Biological water quality parameters totally relates on how and what is the amount of pathogens that are present in the medium. How to calculate these pathogens which are present in the medium, right? Physical water quality parameter include, first one is your suspended solid. First physical water quality parameter is your suspended solids. Next is your turbidity. Next is color. Then we have taste and odor. Then we have taste and odor. And last we have temperature. So all these parameters can be felt and sensed by any of our senses. Hence the name given is physical water quality parameter. Next is the chemical water quality parameter. So chemical water quality parameter will affect the chemical quality of water. So next one is chemical water quality parameter. So chemical water quality parameter includes, first one is your dissolved solids. First one is your dissolved solids. Second is your alkalinity. Then I have pH. Then I have hardness. Next is chloride content. Next is your fluoride content. Next is your nitrogen content. Next one is your dissolved gases. And last one is your metals. So all these are your chemical water quality parameter. And last one, if I talk about the biological water quality parameter, I am talking about how to calculate the count of pathogens that are present in the medium. And when I talk about the count of pathogens, I am talking about the disease causing microorganisms, right? So calculating the total quantity of disease causing microorganisms comes under the biological water quality parameter. So we will going to start with physical water quality parameter. Just 1 minute. So first one is physical water quality parameter. In physical water quality parameter, the first parameter is suspended solids. The first parameter is suspended solids. Usually the suspended solids are present in the water which is extracted from the surface source. So if we are extracting water from any lake, river, ponds, oceans and sea, then in these type of river source or water sources, we usually found suspended solids. The source of suspended solids can be, the sources of suspended solids can be inorganic source. It can be inorganic source, which includes silt and sand or clay. It can be organic source. Which include plant leaves or fibers, or algae. These are the few common examples of organic suspended solids, right? And last one, it can be oil and grease. Last source can be oil and grease. So these are the major sources of suspended solids or causing suspended solids in our water supply. Next, what is the impact that a suspended solid does? So the major impact that a suspended solid does is it makes the water aesthetically displeasing. It makes the water aesthetically displeasing. It means that if I'll give you a water which contains some suspended solids, you might have a psychological effect that I should not consume this water. So this type of psychological effect is known as aesthetically displeasing, means it doesn't looks good. So the first impact that a suspended solid does is it makes the water aesthetically displeasing. So this is the first impact. The second impact that suspended solid does is it provides adsorption sites. It provides adsorption sites to all the chemical or biological reagents. It provides absorption sites to all the chemical or biological reagents. Right? So we add reagents or chemicals. We add biological reagents and chemicals in order to treat this water. So if suspended solid is present like this suspended solids will provide adsorption sites to all these chemicals and biological reagents like this, right? So this reagent which is added in water in order to treat that water, these reagents get adsorbed over the surface of the suspended solids and does not do their actual work, right? Next is, third one is it provides shields or it shields the pathogens, it shields the microorganisms, hence affects the disinfection process, okay? It provides the shielding effect to the microorganisms, hence reduces the disinfection process. And last one is, if your suspended solids are present, it causes incrustation in pipes. It causes incrustation in pipes, right? So we usually use these pipes to take water from one place to the another, right? If the water which is flowing inside this pipe contains suspended solids, if the water which is flowing inside the pipe contains suspended solids, these suspended solids will settle at the bottom of these pipes. These suspended solids will settle at the bottom of these pipes like this, and it reduces the discharge carrying capacity of the pipe, right? You can see here, if these solids are settled like this, earlier the area which is available with the water to flow is this A, right? And once these solids are settled, now the available area is less. It is A dash. This is A dash. The available area reduces. This reduction in area, or due to which the discharge carrying capacity of the pipe reduces, this phenomena is termed as incrustation. That is the settling of the solids at the bottom of the pipe, which reduces the discharge carrying capacity of the pipe. So these are the four major impacts that a suspended solid does if it is present in our water supply. Next, suspended solids are measured using, gravimetric technique. It is measured using gravimetric technique. Whenever we measure the weight of the unknown parameter, it is termed as the gravimetric technique. You need to be clear on this, that suspended solid is a physical water quality parameter. On the other hand, your dissolved solid is a chemical water quality parameter. So your dissolved solid will going to affect only the chemical quality of water, and suspended solid will never affect the chemical quality of water. But once we calculate the suspended solids, we calculate simultaneously. We calculate dissolved solids and suspended solids simultaneously. So how we do? We take two identical samples. We take two identical samples of water. We take two identical samples of water. So this is my sample number 1 and this is my sample number 2. These two are identical samples of water, right? These two are identical samples of water. For first sample, this contains both the suspended solids and the dissolved solids. We just keep this sample in an oven. We just keep this sample in an oven at 104 degrees Celsius for the duration of 24 hours, right? In these 24 hours, at this temperature inside the oven, all the water will evaporate and we will be left with the total solids. It will be both dissolved and suspended solids, right? So we just measure the weight of total solids. We measure the weight of total solids from here, right? We measure the weight of total solids from here. The next sample, which again contains both the dissolved and the suspended solids, what we do is we pass this water through a filter paper. We pass this water through a filter paper, and over this filter paper, all the suspended solids will be retained. All the suspended solids will be retained like this, right? And at the bottom, we get water which contains only dissolved solids. This water will contain only dissolved solid because all the suspended solids are retained over the filter medium, right? We keep this filtrate in an oven. We keep this filtrate in an oven again at 104 degrees Celsius for the duration of 24 hours. For the duration of 24 hours. In this 24-hour duration at 104 degrees Celsius, all the water will going to evaporate and we will be left with only dissolved solids. We will be only left with the dissolved solids. So only dissolved solids will be there, and here we measure the weight of the dissolved solids. We measure the weight of the dissolved solids, right? We measure the weight of the dissolved solids like this, right? This filter paper is never kept in an oven for measuring the quantity of suspended solids, because there are chances that the weight of the filter paper may change, due to which the quantity of suspended solids that you have calculated comes out to be erroneous, that it contains error, okay? So this filter paper is not kept in an oven which contains these suspended solids. We measure the dissolved solids, we measure the total solids, and then using the simple relation that your total solid is equals to suspended solid is equals to suspended solids is equals to suspended solids plus dissolved solids. Suspended solids plus dissolved solids, right? Using this simple relation, you can easily calculate the value of suspended solids. You know the value of total solids, you know the value of dissolved solids. From here, you can easily calculate the value of suspended solids, okay? So this is the first classification of total solid, that it includes suspended solids and dissolved solids. Now, depending upon whether the solid is organic solid or inorganic solid, we have one more classification for that. So total solid is again of two types. Total solids is again of two types: organic or volatile solids, organic or volatile solids, organic or volatile solids, or we will going to have inorganic or fixed solids, inorganic or fixed total solids, right? Same classification we have for suspended solids and dissolved solids also. So for suspended solids, we have organic or volatile suspended solids or fixed or inorganic suspended solids. Similarly, for dissolved solids, we have organic dissolved solids and inorganic dissolved solids, okay? So this, now how to get this classification done and how to calculate the exact value of organic or volatile solids or inorganic solids, right? So what we do is, here, that is the oven dried sample for the total solids. This oven dried sample for the total solid, it is kept in muffle furnace. it is kept in muffle furnace, it is kept in muffle furnace, it is kept in muffle furnace at 550 to 600 degrees Celsius, at 550 to 600 degrees Celsius for the duration of 2 hours. At this high temperature and for this duration of time, all the volatile fraction or the organic fraction of the solids will going to vaporize, and we are only left with the inorganic or fixed solids. So here we can easily calculate the weight of inorganic total solids. Inorganic total solids, right? We can easily calculate the weight of inorganic total solids. We know the weight of total solids. We know the weight of total solids. So total solids is equals to volatile or organic total solid plus fixed or inorganic total solids, right? We know the value of total solids, we know the value of fixed inorganic total solids. I can easily calculate the value of volatile organic total solids, right? I can easily calculate the value of volatile total solid or organic total solid, right? Now, how to get same classification for suspended solids and dissolved solids? So what we do is, we have this oven-dried sample for dissolved solid. We keep this oven-dried sample of dissolved solid again in the muffle furnace at 550 to 600 degrees Celsius for the duration of 2 hours. And this duration, all the organic fraction will going to vaporize, and we will be left with the fixed or inorganic solids, right? So we have the value of inorganic dissolved solids after keeping it in the muffle furnace. So again, using a simple relation, we can easily calculate the value of organic dissolved solids. So your dissolved solids is equals to organic dissolved solids plus inorganic dissolved solids, right? So I know the value of dissolved solids, I know the value of inorganic dissolved solids, I can easily get the value of organic dissolved solids likewise, okay? Now, for calculating the organic suspended solid and inorganic suspended solid, we will not going to keep the filter paper inside the muffle furnace, because if we do so, what will going to happen is that filter paper will only going to burn, right? And that will not going to give us the exact value of the suspended solids in inorganic form, right? So what we do is, using these two relations, right? So using dissolved solids, we have the value of inorganic dissolved solids and organic dissolved solids. Using total solids, I have the value of organic total solids and inorganic total solids, right? Now what I want the value of organic suspended solids and inorganic suspended solids, right? So these are the two things that I want to calculate. So what I will do is, I will just add your organic total solid, please mark it as important, your organic total solid is equals to organic suspended solid plus organic dissolved solids, right? So I know the value of organic dissolved solids, so I know this. I know the value of organic total solid, I know this. I can easily calculate the value of organic suspended solids. Now, building the same relation, one more thing I know, my inorganic total solid is equals to inorganic suspended solids plus inorganic dissolved solids, right? So here also I know the value of inorganic total solids, I know the value of inorganic dissolved solids, I can easily calculate the value of inorganic suspended solids. So using all these relations, I have any type of solid which is present in the medium. I know concentration of any variety of solid which is present in the medium. So if I'll just summarize all these equations, right? So first one is total solid is equals to suspended solid plus dissolved solid. Next is total solid is also equal to inorganic total solid plus organic total solid. Next, your suspended solid is equals to inorganic suspended solid plus organic suspended solid. Next, your dissolved solid is equals to inorganic dissolved solid plus organic dissolved solid. Next, I know inorganic total solid is equals to inorganic suspended solid plus inorganic dissolved solids. Next, I know organic total solid is equals to organic suspended solid plus organic dissolved solids. So using all these relations, I can easily calculate the value of any type of solid which is present in the medium. The most important part regarding this parameter is the question is given in the experiment form, right? Your entire experiment will be explained in the question, and you need to identify what all quantities are given to you and what all quantities you need to calculate. Is this okay? Is this okay from your end? Is this okay from your side? Okay, next. So this is the first physical water quality parameter. The first physical water quality parameter is the suspended solids. Okay. When I talk about the permissible limit, so for according to NEFA, according to NEPHA, National Environment Protection Act, NEFA, the permissible limit of suspended solid, permissible limit of suspended solids, is equal to 30 milligram per liter. It is equal to 30 milligram per liter. So this is the permissible limit of suspended solids according to National Environment Protection Act. Right? So you can just remember this value directly, because again a statement can be formed regarding the permissible limit of suspended solids. Please mark this word, suspended solids, right? This is for suspended solids, not for total solids, not for dissolved solids. I'm talking about suspended solids. If I talk about total solids, acceptable limit is 500 milligram per liter. Acceptable limit is 500 milligram per liter, right? That we need to treat the water in which the total solid concentration should be less than 500 milligram per liter. 500 milligram per liter is the acceptable limit, and cause for rejection value is 2000 milligram per liter. Cause for rejection value is 2000 milligram per liter. 2000 milligram per liter, right? What do we mean by cause for rejection value? During emergency or during war situation where the water cannot be treated, right? Where the water cannot be treated and we want more amount of water to be treated, then in that situation we can extend the value of total solids up till 2000 milligram per liter during emergency situation, like when any flood happens or any war happens, any disaster has came or hit a place. Then in that case, for some duration of time, when the treatment plant is not operational or a treatment plant is having some problem, then in that case you can have the water which has the total solid concentration of 2000 milligram per liter. So this is the value of your cause for rejection value for your total solids, right? So this is all about your first physical water quality parameter, total solid. Next physical water quality parameter is your turbidity. We all have read that if this is my medium, which contains water and it also contains solids, right? It also contains solids. If any ray of light is incident over these solids, the path that is traveled by ray of light, it gets scattered like this. This scattering of light after hitting the suspended solids is termed as Tyndall effect. It is known as Tyndall effect, right? The quantity by which these lights are either scattered or absorbed by this medium is termed as turbidity of the medium. So what is turbidity? It is the amount by which these lights are either scattered or absorbed by the medium, right? Turbidity is caused by the suspended solids. Suspended solids only cause turbidity of the water sample, but these suspended solids cannot be related quantitatively with the turbidity of the water. What I mean to say is, if you consider two water sample like this, right? Say both the samples having same concentration, say X milligram per liter of suspended solids, and other also has X milligram per liter of suspended solids. Both the sample contains same concentration of suspended solids. But the thing is, for the first sample, the particles are more distributed and lesser in size, right? The particles are more distributed and lesser in size. But for the second sample, your particles are of larger size. Your particles are of larger size like this, right? So for this second sample, your turbidity of the water will be less, right? Because the exposed surface area is more for fine particles. Your exposed surface area is more, means more scattering of light will going to happen, due to which this first water sample will going to have more turbidity. So for first sample, your turbidity will be more. Turbidity for sample 1 will be more than turbidity for sample 2. Turbidity for sample 2, okay. Turbidity is a function of the amount of surface of the suspended solids that are available. If the exposed surface area of the suspended solids is more, then those suspended solids will going to cause more turbidity in the water sample, okay. So turbidity is caused by suspended solids, but it cannot be related quantitatively with the suspended solids. Next. So all the sources of suspended solids are the sources of turbidity. All the impacts of suspended solids are the impact of turbidity, including one more impact, right? And what is that? If you consider a lake which has high turbidity, if you consider a lake like this which is having high turbidity, right? This lake has high turbidity. Then what will happen is, whatever sunlight is coming to this lake, right, which is having high turbidity, it does not reaches to the bottom of the lake where the aquatic plants are present. It does not reaches to the bottom of the lake where the aquatic plants are present. And if the sunlight does not reaches to the bottom of the lake where aquatic plants are present, then no photosynthesis will happen for these aquatic plants, right? And we know that from photosynthesis, oxygen is released. And if this photosynthesis will not be happening, then no oxygen will be released by these aquatic plants. So what we see is, we see the fall in level of dissolved oxygen. We see fall in level of the dissolved oxygen. We see fall in level of the dissolved oxygen in this lake, right? Because photosynthesis is not happening for this lake due to more turbidity. So along with all the impacts that we have read for suspended solids, along with it for turbidity, we have one more impact, that if a lake water is turbid, it will going to affect the penetration of sunlight till the bottom of the lake where aquatic plants are present. Hence, no photosynthesis will take place, due to which your dissolved oxygen level inside the lake will going to decrease, right? So this is again one of the impact for turbidity. Next is measurement of turbidity. Measurement of turbidity. So turbidity can be measured by turbid rod method. turbid rod method. It can be measured by Jackson's turbidity meter. It can be measured by Jackson's turbidity meter. It can be measured by Baylis turbid meter. Baylis turbid meter. It can be measured by Baylis turbid meter, or it can be measured by nephelometer. It can be measured by nephelometer, right? Now, for turbidity rod method and Jackson's turbidity meter method, we measure the path, length of path. We measure the length of path. We measure the length of path traveled by light. Length of path traveled by light. Traveled by light. We measure the length of path traveled by light. The unit in which we measure the turbidity is STU, silica turbidity unit. The standard samples are prepared using Fuller's earth. The standard samples are prepared using Fuller's earth or SiO2, right? So, standard samples are prepared using Fuller's earth or SiO2. Next, for Baylis turbidity meter method and nephelometer, these both are based on color matching technique. These both are based on color matching technique. Color matching technique. Color matching technique. These both are based on color matching technique. These both are based on color matching technique. But the Baylis turbidity meter method is based on the absorption phenomena. It is based on the absorption phenomena, whereas your nephelometer is based on the scattering principle. It is based on the scattering principle, right? For Baylis turbidity meter method, again the unit in which the turbidity is measured is STU, silica turbidity unit, and for nephelometer, the turbidity is measured in NTU, nephelo turbidity unit. And here the color is developed for NTU, the color is developed using formazine. The color is developed using formazine. The color is developed using formazine, right? So, this is the basic outline how the turbidity is measured using all the four methods. If I talk about what is the method that is currently used for measuring the turbidity, so it is the nephelometer. And nowadays, all the turbidity is measured in NTU through nephelometer, okay. If I talk about the permissible limit for turbidity, so for turbidity, acceptable limit is 1 NTU. Acceptable limit is 1 NTU. It is 1 NTU. And cause for rejection value is 5 NTU. Cause for rejection value is 5 NTU. All these things has to be kept in your mind, right? So, this is the acceptable and the cause for rejection value for turbidity in your water sample. So, this is your second physical water quality parameter. The next physical water quality parameter is color. So, basically, color is caused by the presence of iron and manganese. If iron and manganese is present in your water, it will going to impart color, right? It will going to impart color to your water. The color is measured by color matching technique. It is measured by color matching technique. It is measured by color matching technique. Color matching technique. It is measured by color matching technique, and the color is developed using platinum. Color is developed using platinum in the form of chloroplatinate ion. In the form of chloroplatinate ion. In the form of chloroplatinate ion. In the form of chloroplatinate ion, right? So color is developed using platinum in the form of chloroplatinate ion. Color is measured using the color matching technique, right? So the equipment in which the color is measured is termed as tintometer. The equipment in which the color is measured is termed as tintometer. Is this okay? So the permissible limit for color is, acceptable limit is 5 TCU. Acceptable limit is 5 TCU, that is true color unit or Hazen's unit. So TCU is true color unit. It is true color unit. It is true color unit or Hazen's unit. Or Hazen's unit. True color unit or Hazen's unit, right? Cause for rejection value is 25 TCU. Cause for rejection value is 25 TCU. So you can keep a check on all the things that are written for this parameter on this board, so that if any question is there, you can easily answer with respect to the color. So iron and manganese are the main elements that are causing to color to your water supply, right? And iron and manganese are present whenever you extract underground water. So this underground water can be free from suspended solids, but it will always have some color due to the presence of iron and manganese. Is this clear to you? Is this clear? Okay. Let's just keep moving. Next is taste and odor. Taste and odor. Next is taste and odor. And taste and odor is measured using dilution. It is measured using dilution. It is measured using dilution, right? It is measured using dilution. So what we do is, we take water sample like this. We have this water sample like this, right? So we have this water sample in which 10 ml of the water is there. 10 ml of water sample we have taken. Now this water contains taste and smell. Sorry, taste and odor. Yes, smell. This water contains taste and odor. So what we do is, we just take 1 ml of this water and we supply it to the another tube. We supply it to the another tube like this, right? We supply this to the another tube. I have taken 1 ml of this. I have taken 1 ml of this original water and I have supplied it, and I have added 9 ml of aerated water from our side. So this tube, second tube, contains 1 ml of water sample plus 9 ml of aerated water. 9 ml of aerated water to again make the volume as 10 ml, right? So for this also, we have diluted it till 10 ml by adding 9 ml of aerated water. So what we do is, we again smell this water, diluted water, and if this diluted water is free from taste and odor, we represent taste and odor in terms of the dilution ratio or dilution factor. So this dilution factor or dilution ratio can be calculated as final volume of the diluted sample. Dilution ratio is the final volume of the diluted sample. Final volume of the diluted sample. Final volume of the diluted sample. Final volume of the diluted sample divided by volume of original sample, volume of original sample present in diluted sample, volume of original sample present in diluted sample, right? So for this diluted sample, the final volume is 10 ml and the volume of original sample that is present in this diluted sample is 1 ml. So for this, the dilution ratio comes out to be 10 by 1, that is 10. Okay. So accordingly, you can calculate the dilution ratio and you can represent the taste and odor through this dilution ratio. So whatever dilution ratio you are getting for the diluted sample which is free from taste and odor, that is represented as taste and odor for that. So, so the unit in which taste and odor is represented is known as threshold odor number, threshold odor number, threshold odor number, that is TON. Threshold odor number, that is TON. Threshold odor number, that is TON, right? Threshold odor number, that is TON. So hopefully you are getting all these parameters correctly. Just give me a second. So acceptable limit is 1 TON, that is whatever water sample you are taking, it should be free from taste and odor, and cause for rejection value is 3 TON. Cause for rejection is 3 TON. 3 TON. So TON is the threshold odor number that is used as a unit for representing the taste and odor. The equipment in which this dilution is done is known as osmoscope. Osmoscope is the equipment through which we measure the dilution of the water sample, right? So this is all about the parameter taste and odor. The last physical water quality parameter is your temperature. So temperature is easy. Temperature is measured using thermometer. It is using thermometer. It is measured using thermometer. And for our raw water supplies, it is maintained in the range of 10 to 25 degrees Celsius. It is maintained in the range of 10 to 25 degrees Celsius. So hopefully you have understood all these physical water quality parameters. After the break of 5 minutes, we will going to start with the chemical water quality parameters. So welcome back. We have discussed about all the physical water quality parameters. Next, we will going to discuss about the chemical water quality parameters. So for chemical water quality parameter, first we have is the dissolved solids, right? First chemical water quality parameter is dissolved solids. We have already seen how these dissolved solids are calculated accurately. So these dissolved solids are calculated using gravimetric technique. These dissolved solids are calculated using gravimetric technique. Gravimetric technique. These dissolved solids are calculated using gravimetric technique, right? We have one more approximate method for calculating these dissolved solids. So these dissolved solids can be calculated approximately. They can be calculated approximately by measuring the specific conductance of the water. By measuring the specific conductance of the water. If we measure the specific conductance of the water, then your dissolved solid concentration can be calculated as a specific conductance multiplied by the factor of 0.65. This specific conductance should be in micromole per centimeter. This specific conductance should be in micromole per centimeter. So if we keep the value of specific conductance in micromole per centimeter and multiply it with 0.65, the amount of dissolved solids we will going to get will be in milligram per liter. This will be in milligram per liter. So again, this is an approximate method for measuring the dissolved solid concentration of your water sample, right? Next chemical water quality parameter is alkalinity. So alkalinity is the property by which water neutralizes the acid. It is the acid neutralizing capacity of water. So if we need to neutralize the acid, this acid can be neutralized only by the anions present in the medium. So alkalinity is the basic property of the anions that are present in the medium. So alkalinity is the acid neutralizing capacity of water. It is the acid neutralizing capacity of water, and acids can be neutralized. These acids, H plus ions, can be neutralized only by the anions, right? So basically, alkalinity is the property of the anions, that is the negatively charged particles. If I talk about the alkalinity, so all the anions that are present in the medium will going to cause alkalinity, but majorly we consider three types of anions only, right? So all the anions will going to cause alkalinity, but for our water sample we consider three anions. First one is the OH minus ion. Alkalinity caused by the OH minus ion is termed as caustic alkalinity. It is termed as caustic alkalinity. Next is CO3 2 minus ions. CO3 2 minus ions. The alkalinity caused by CO3 2 minus ions is known as carbonate alkalinity. And last one is the alkalinity caused by HCO3 minus ions. HCO3 minus ions is known as bicarbonate. Bicarbonate alkalinity, right? So these are the three different types of alkalinity that are majorly present in our water sample. Now, how to calculate these alkalinity? These alkalinities are measured by the technique of titration. These alkalinities are measured by the technique of titration. The titrant used is 0.02 normal H2SO4. titrant used is 0.02 normal H2SO4, and the indicators used are, first one is phenolphthalein, and second one is methyl orange. These are the two indicators that are used for performing this titration. Now, when we start the titration, if I plot a graph between pH of the water sample, if I plot a curve between pH of the water sample, let me just draw this curve. So on the x-axis, I have plotted the volume of acid used. This is the volume of acid used. Volume of acid used in ml. And on the y-axis, I have plotted the pH of the water sample. So first, the pH of the water sample is taken up to 10, it is maintained at 10, and we start performing the titration over our water sample for calculating the alkalinity. At 10, at pH of 10, we add phenolphthalein indicator and we start our titration. So from pH 10, the pH starts falling and it falls up to a level of 8.2. 8.2. This is a pH of 8.2, where we see the first color change of the phenolphthalein indicator. So this is our first stage of titration, and in first stage of titration, phenolphthalein indicator was used. In the first stage of titration, all the caustic alkalinity will be removed, and half of the carbonate alkalinity will be removed. In the first stage. Now at a pH of 8.2, I'll add methyl orange indicator and continue with the titration, and I'll continue with the titration. So at a pH of 4.5, at this pH of 4.5, I'll again get a second color change. So this is a pH of 4.5 and I'll get a second color change. So this is my second stage of titration. This is my second stage of titration, right? This is my second stage of titration. Here the here the indicator used is methyl orange, and in the second stage, remaining half of the carbonate alkalinity and all the bicarbonate alkalinity are removed. Remaining half of the carbonate alkalinity and all the bicarbonate alkalinity are removed. Okay. Volume of acid used for doing the first stage or completing the first stage is P, and M is the total volume of acid used. M is the total volume of acid used for performing the titration, right? So as you can see here in the graph, in the first stage, all the caustic alkalinity and half carbonate alkalinity is reduced. Now why I am saying half of carbonate alkalinity? Because in first stage what happens is, this carbonate that is present, it reacts with the acid added and it gets converted into bicarbonate. Right? So this is the bicarbonate which is converted from carbonate ions. Then we have another bicarbonate which was originally present in the medium. So this bicarbonate that is formed, this bicarbonate is reduced in the second stage. This bicarbonate which is formed due to the carbonate is reduced in the second stage. One point more you need to check, that this caustic alkalinity, OH minus ion, this caustic alkalinity and bicarbonate alkalinity are not neutralized simultaneously. Caustic alkalinity is neutralized in the first stage, whereas bicarbonate alkalinity is neutralized in the second stage. Is this okay? So this is the entire neutralization of all the types of alkalinity that are present in the medium. Thank you, Pragya sir. Thank you so much. So for first stage, the indicator used is phenolphthalein. For second stage, the indicator used is methyl orange. Is this okay? Now, when we talk about these indicators, right? These indicators give the color change. This indicator gives the color change. Phenolphthalein gives the color change because it comes out from its working range. It comes out from its working range. It comes out from its working range. Phenolphthalein has a working range of 10 to 8.5. It has a working range of 10 to 8.5. That's why when at pH of 8.2, you get a color change for phenolphthalein, whereas for methyl orange, it enters into its working range. It enters into its working range. Into its working range. It enters into its working range. And the working range for methyl orange is 4.5. It is 4.5 to 2.3. This is the working range for methyl orange. Is this okay? So this is, you need to keep a check on which indicator is reducing which alkalinity, right? So phenolphthalein is the indicator that is reducing caustic alkalinity and half of carbonate alkalinity. Methyl orange indicator is used to reduce all the bicarbonate alkalinity and the another half of carbonate alkalinity, right? Next, if P is the volume of acid used in stage 1 and M is the total volume of acid used, so I have different cases. If case 1, so I'll write C1, if P is equal to 0 and M is non-zero, it means that the volume of acid used in stage 1 is 0. It means that volume of acid used in first stage, volume of acid used in first stage is 0. It means that no caustic and carbonate alkalinity is present. It means that only bicarbonate alkalinity is present. Only bicarbonate alkalinity is present. Only bicarbonate alkalinity is present, right? So this is my case number 1. Case number 2 is, if P is equals to M, it means that volume of acid used in second stage is 0. It means that volume of acid used in second stage volume of acid used in second stage is 0, and we only have caustic alkalinity in the medium. So only caustic alkalinity will be present. Only caustic alkalinity will be present. Only caustic alkalinity will be present, right? Next, case 3. If P is equals to M by 2, it means the volume of acid used in first stage is same as the volume of acid used in the second stage. Good evening, Atul sir. And if P is equals to M by 2, then only carbonate alkalinity is present. Then only carbonate alkalinity is present. Carbonate alkalinity is present. Case 4, if P is more than m by 2, it means that volume of acid used in stage 1 is more than stage 2. It means that volume of acid used in stage 1 is more, volume of acid used in stage 1 is more. It means that in your medium, caustic and carbonate alkalinity are predominant. Caustic and carbonate alkalinity are predominant, right? On the other hand, if P is less than m by 2, case 5, if P is less than m by 2, it means that volume of acid used in second stage is more. Volume of acid used in second stage, volume of acid used in second stage is more. It means that your carbonate and bicarbonate alkalinity are predominant. Your carbonate and bicarbonate alkalinity are predominant. So carbonate and bicarbonate alkalinity are predominant. Your carbonate and bicarbonate alkalinity are predominant. Okay. So these are the 4 cases depending upon the volume of acid used in stage 1 and stage 2, and you need to keep a check that which type of alkalinity is present in the medium. Keeping the value of P and M, we have 5 different cases, right? And we have checked that what all alkalinity will be present in the medium. So you can just note down these things. Now alkalinity is represented as calcium carbonate. Alkalinity is represented as calcium carbonate. So alkalinity is represented as calcium carbonate, right? So what we do to calculate alkalinity? First we calculate the number of gram equivalents of all the entities causing alkalinity, we calculate the number of gram equivalents of all the entities causing alkalinity, and we multiply it with the equivalent weight of CaCO3. We multiply it with the equivalent weight of CaCO3, right? Now, how to calculate number of gram equivalents? So, number of gram equivalents can be simply calculated as number of gram equivalents is equals to the given weight divided by the equivalent weight right, of the particular substance. So this will going to give us the number of gram equivalents of a particular substance. Now how to calculate the equivalent weight? So equivalent weight is nothing but the molecular weight divided by valency. It is the molecular weight divided by the valency. Molecular weight divided by the valency will be your equivalent weight, right? So you can easily calculate the alkalinity as CaCO3. So for suppose if you are given with the OH minus ions concentration and you are given with the carbonate ion concentration, so first of all you need to calculate the number of gram equivalents of OH minus ion, then calculate the number of gram equivalents of carbonate ions, add both the number of gram equivalences. So you will have total number of gram equivalents of alkalinity and multiplied with the equivalent weight of CaCO3. Okay, so that is how you can calculate the total alkalinity. If you need to determine alkalinity only because of OH minus ion, so what you have to do is you have to calculate the number of gram equivalents of OH minus ion and multiply it with the equivalent weight of CaCO3. That will going to give you the concentration of alkalinity caused by OH minus ion or the caustic alkalinity. Okay, so likewise you can calculate alkalinity from all these entities, or even you can calculate the total alkalinity of the medium like this. Is this okay? Is this fine? Is this fine? Any doubt in this? Chalo, moving on with this. The next chemical water quality parameter is pH, right? And we know that pH is nothing but the negative logarithm of H plus ion. First of all, the acceptable limit for alkalinity is 200 milligram per liter as CaCO3. 200 milligram per liter as CaCO3. Then cause for rejection value for alkalinity is 600 milligram per liter as CaCO3. So these are the permissible limits for this alkalinity, right? So these are the permissible limits for alkalinity. These are the permissible limits for alkalinity of your water sample. Alkalinity is caused by the anions, that are the negatively charged ions, right? And alkalinity is the property of the anions. Because of the anions, alkalinity is caused for a water sample. Okay. So next chemical water quality parameter is pH. And we know that pH is nothing but negative log to the base 10 of H plus ion concentration. It is negative logarithm of the H plus ion concentration. pH is the scale to measure the acidity and basicity of your water sample, right? So pH is a scale to measure acidity and basicity of your water sample. Again, we have one more term which is known as POH. So POH is nothing but negative log to the base 10 of OH minus ion concentration. So this is how you can calculate pH and POH. Now here the H plus ion concentration and the OH minus ion concentration, both of these concentrations should be kept in moles per liter. Both of these concentrations should be kept in moles per liter in order to calculate pH or POH of the system, right? We have one more relation, that is pH plus POH is equals to 14. And we also know that H plus ion concentration multiplied by OH minus ion concentration is equals to 10 raised power minus 14, right? So this is the H plus ion concentration and the OH minus ion concentration product, and this product is also known as the Rn product, right? This product is also known as the Rn product. pH is measured using potentiometer. It is measured using potentiometer. It is measured using potentiometer using calomel electrodes. Using calomel electrodes. Using calomel electrodes, right? Using calomel electrodes. Using calomel electrodes, we calculate the pH. Now, what is the special about these calomel electrodes? These calomel electrodes are only sensitive towards H plus ion and OH minus ion. No other ions can attract or get attached over these calomel electrodes. only the H plus ion and the OH minus ion, these calomel electrodes are sensitive to, right? So potentiometer is used to measure the pH of the water sample using calomel electrodes, and these calomel electrodes are only sensitive towards H plus ion and OH minus ion, right? Next, if we are measuring pH, if you are measuring pH using indicators, and in indicators you are using bromothymol blue, then for this bromothymol blue, if you are using as an indicator to measure the pH, this equipment is known as aquascope. So aquascope is an equipment. This is an equipment where we use bromothymol blue as an indicator to measure the pH of our water sample. Is this okay? So you can keep all these things in mind because you may get a direct statement from all the properties of these chemical water quality parameters. Okay. Now talking about the permissible limit. So acceptable limit for pH is, for pH is 6.5 to 8, it is 7 to 8.5, it is 7 to 8.5. This is the permissible limit of pH in our water sample. Now one more thing I would like to discuss. Usually there is a statement that can water be acidic and alkaline at the same time? So here I have the solution for that. If I draw this pH scale from 0 to 14, so this is 0 to 14, and somewhere in the between we have this neutral, right? So this is my neutral. On the left side of the neutral, water is acidic, and on the right side of the neutral, water is basic. But just now we have performed one titration and we have seen that all the alkalities are reduced at pH of 4.5. So we are reducing alkalinity up till the pH of 4.5, right? So at pH of 4.5, my carbonate alkalinity is reducing. So till pH 4.5, alkalinity is present in the medium. So here we have a range between 4.5 to 7 where the water is both acidic and alkaline at the same time. Water is both acidic and alkaline at the same time between this pH of 4.5 to 7, right? So water can be acidic and alkaline at the same time. You need to keep a check on this. Water can be acidic and alkaline at the same time from the pH of 4.5 to 7. Okay, so hopefully this is clear to you. Next. Next chemical water quality parameter is your hardness. So hardness is basically a property of multivalent cations. It is the property of multivalent cations. That is ions which are having +2 and +3 charges. So ions that are having +2 or +3 charges causes hardness to your water, right? So hardness is the property of multivalent cations, and when I talk about multivalent cations, I am talking about those ions which have +2 or +3 charges, right? If hardness is present in the water, it reduces the foam forming ability of the soap, right? If hardness is there in the water, it reduces the foam forming ability of the soap. So if you consume hard water or you take hard water in use, obviously your soap consumption will going to increase, right? So hardness is caused by the multivalent cations, and in this and what do we mean by multivalent cations? These are +2 or +3 charge positive ions. Okay. Next is the major ions that causes hardness in water includes magnesium ion and calcium ions. These are the major ions. These are the major ions that are causing. These are the major ions that are causing hardness to your water sample. All the remaining multivalent cations causes hardness, but the concentration of these ions are in major quantity, right? Hardness is of two types. First type of hardness is carbonate hardness. First type of hardness is carbonate hardness. So what do we mean by carbonate hardness? The carbonates and bicarbonates of all the multivalent cations causes carbonate hardness. So carbonate hardness is caused by the carbonates and bicarbonates of carbonates and bicarbonates of multivalent cations. Multivalent cations, right? Multivalent cations. So this causes your carbonate hardness. Some of the example of carbonate hardness are MgCO3. Compound called MgCO3 will going to cause carbonate hardness. Then you have MgHCO3 whole twice. Then you have CaCO3. Then you have CaHCO3 whole twice. So all this will going to cause hardness or carbonate hardness to your water sample. So this is the first type of hardness which is caused by carbonates and bicarbonates of the multivalent cations. It is known as the carbonate hardness. The next type of hardness is known as the non-carbonate hardness. Non-carbonate hardness. Non-carbonate hardness. Right. Non-carbonate hardness is caused by the other compounds of these multivalent cations. So apart from carbonate and bicarbonate of these multivalent cations, what all other compounds are there, they will going to cause your non-carbonate hardness. Okay, they will going to cause the non-carbonate hardness. Non-carbonate hardness is also known as the permanent hardness. It is also known as the permanent hardness. It is also known as the permanent hardness, whereas your carbonate hardness is known as the temporary hardness. It is known as the temporary. It is known as the temporary hardness, right? This hardness is measured. This hardness is measured using titration. This hardness is measured using titration, and titrant used is EDTA. Titrant used is EDTA. Titrant used is EDTA. That's why it is also known as EDTA method. Indicator used is EBT. Indicator used is EBT, eriochrome black tea. Indicator used is EBT, that is eriochrome black tea, right? The color change that we will get, color change that we will get will be equal to, or the color change will be from wine red. The color change will be from wine red to blue black. Color change will be from wine red to blue black. So this is the color change that we will get for this titration, right? So these are the details of the titration. Now calculating the hardness of the water sample. So hardness of the water sample is equals to the volume of EDTA used. Volume of EDTA used volume of EDTA used multiplied by the normality of EDTA, multiplied by the normality of EDTA, normality of EDTA, right? Now what we are doing? We are just calculating the number of gram equivalents of EDTA used, and that will be equal to the number of gram equivalents of the hardness present in the system, right? So we are just equating the number of gram equivalents. So I will write a direct statement that number of gram equivalents of EDTA used, number of gram equivalents of EDTA used will be equal to number of gram equivalents will be equal to the number of gram equivalents of hardness, right? Now in order to calculate the concentration of hardness, this number of gram equivalents of EDTA is multiplied by the equivalent weight of CaCO3. It is multiplied by the equivalent weight of CaCO3. It is multiplied with the equivalent weight of CaCO3, right? RF is saying hello, 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 RF. Okay. So hardness can be calculated as number of gram equivalents of EDTA multiplied by the equivalent weight of CaCO3. Moving on with this, the permissible limit for hardness is, acceptable limit is 200 milligram per liter. Acceptable limit is 200 milligram per liter as CaCO3, and cause for rejection value is 600 milligram per liter as CaCO3. 600 milligram per liter as CaCO3. So these are the permissible limits for hardness of your water sample. These are the permissible limit for hardness of your water sample. Next, write down one note point that minimum of alkalinity and total hardness, is equal to the carbonate hardness, The minimum of alkalinity and total hardness is equal to the carbonate hardness, right? So the minimum of alkalinity and total hardness will be equal to the carbonate hardness of the medium. Next, if sodium alkalinity is present, then your non-carbonate hardness will be absent. Right? So these are all the details regarding the hardness of your water sample. You need to keep a check on all these parameters that are causing hardness. Next, so this was all about hardness. Next chemical water quality parameter is the chloride content. So fifth one is the chloride content. Next is your chloride content, right? So if chloride is present in your water, it means that the water is polluted by any industry or any sewage. If your chloride is present in water, then that water is polluted by any industry or sewage. Chloride content is determined using, it is measured using titration. It is measured using titration. It is measured using titration, and this method of titration is known as Moore's method. It is known as Moore's method. This method of titration is known as Moore's method. So Moore's method is used to determine the chloride content, right? So what we do is, the chloride that is present in our water sample, we add silver nitrate, AgNO3, in our water sample, right? So first this silver nitrate will going to react with chloride content and it will going to form a precipitate of AgCl, right? Once this entire chloride is consumed by this silver nitrate, now this silver nitrate will start reacting with potassium chromate, that is K2CrO4. It starts reacting with potassium chromate, which is added as an indicator. This is added as an indicator, right? It starts reacting with potassium chromate. So this silver nitrate reacting with potassium chromate will form a red-brown PPT of silver chromate. It will form a red-brown PPT of silver chromate. So we have a red-brown PPT of silver chromate. This is red-brown PPT of silver chromate. This PPT of AgCl is of white color. So when we get a PPT of red-brown color, it means that all the chloride that is present in the medium has been utilized by silver nitrate, okay? So if you are getting the white PPT of silver chloride, it means that still chloride is present in the medium. If you start getting the red-brown PPT of silver chromate, it means all the chloride that was present in the medium was utilized. Now the silver nitrate is reacting with our indicator, right? So how to calculate the chloride content? We calculate number of gram equivalents. So chloride content is equals to number of gram equivalents of silver nitrate used, number of gram equivalents of silver nitrate used, multiplied by the equivalent weight of chloride, multiplied by the equivalent weight of chloride. So this is how we calculate the chloride content, and here the chloride content will be in milligram per liter. Here the chloride content will be in milligram per liter. So hopefully you are understanding all of this. The chloride content will be in milligram per liter. The permissible limit for chloride in water is, your acceptable limit is 200 milligram per liter, 200 milligram per liter as chloride, and cause for rejection value is and cause for rejection value is 1000 milligram per liter. It is 1000 milligram per liter as chloride ions, right? It is 1000 milligram per liter as chloride ions. So this is about the chloride concentration. Next chemical water quality parameter is fluoride. Next chemical water quality parameter is fluoride. When we talk about fluoride, up till 1 milligram per liter of fluoride is required by us for the proper growth of permanent teeth. Up till 1 milligram per liter of fluoride is required for the proper growth of permanent teeth. For the proper growth of permanent teeth. For the proper growth of permanent teeth, up to 1 milligram per liter of fluoride is required. But if this fluoride exceeds 1.5 milligram per liter, if this fluoride exceeds 1.5 milligram per liter, it starts decolorizing our teeth, which is known as mottling of teeth. It starts decolorizing our teeth, which is also known as mottling of teeth, right? So till 1 milligram per liter, fluoride is required, but if this fluoride concentration exceeds 1.5 milligram per liter, it starts decolorizing our teeth, which is known as mottling of teeth. So the permissible limit for fluoride ranges between 1 to 1.5, right? The permissible limit for fluoride ranges between 1 to 1.5. If this fluoride concentration exceeds 5 milligram per liter, if this fluoride concentration exceeds 5 milligram per liter, it leads to a disease known as bone fluorosis. It leads to a disease which is termed as bone fluorosis, right? So bone fluorosis is caused when your fluoride concentration exceeds 5 milligram per liter. Okay, so this was all about fluoride. When we talk about measurement of fluoride, fluoride is measured using color matching technique. Fluoride is measured using color matching technique, and the color is developed by fluoride is measured using color matching technique. It is measured by color matching technique. And the color is developed using zirconium ion and alizarin. So color is developed by zirconium ion and alizarin. So fluoride is measured by color matching technique, and the color is developed by zirconium ion and alizarin. Okay. Permissible limit for fluoride is permissible limit for fluoride is 1 to 1.5 milligram per liter. So this is the permissible limit of fluoride. Up till 1 milligram per liter of fluoride we require for the proper growth of our teeth and permanent teeth. And if this fluoride concentration exceeds 1.5 milligram per liter, it leads to a disease which is known as mottling of teeth, that is decolorization of teeth. Okay, so hopefully this fluoride concentration is clear to you. Next chemical water quality parameter is nitrogen content. So nitrogen can be present in 4 forms. First form is free ammonia. Free ammonia can be determined using by simple boiling. By simply boiling our water sample and just calculating and measuring the total amount of ammonia liberated, we can measure free ammonia. So by simple boiling, we can measure free ammonia, right? Next is your organic ammonia. So organic ammonia can be measured by adding a strong oxidizing agent to the already boiled sample. We have this already boiled sample for measuring the free ammonia. We add the oxidizing agent and we again boil the sample. So it can be measured by adding strong oxidizing agent, can be measured by adding strong oxidizing agent, strong oxidizing agent, strong oxidizing agent to the already boiled sample. To the already boiled sample, right? And by just counting or measuring the total amount of ammonia that is liberated after adding the strong oxidizing agent, that corresponds to organic ammonia. Free ammonia and organic ammonia is commonly known as Geldahl's ammonia. Free ammonia and organic ammonia is commonly known as Geldahl's ammonia. Third is your nitrite. Third is your nitrite. And if nitrite is present in your water sample, it indicates that partially decomposed organic matter is present. It indicates that partially decomposed organic matter, partially decomposed organic matter is present. Partially decomposed organic matter is present, right? And if partially decomposed organic matter will be there, it means that microorganisms will be there. Sir, effect of fluoride teeth or kya hai sir? Effect of fluoride, first is it causes decolorization of teeth. Second effect, it causes bone fluorosis, right? Where the shape of the bone changes, your bone becomes weak. That is the bone fluorosis. Is this clear? Okay. So we are talking about nitrogen content. The fourth one is nitrogen can be present in the medium in the form of nitrate. In the form of nitrate. And we know that this nitrate is the stable end product. So this nitrite is NO2 minus, it is NO2 minus, and nitrate is NO3 minus, right? So this nitrate, presence of nitrate in a water sample indicates that we have completely decomposed organic matter. We have completely decomposed organic matter. We have completely decomposed organic matter present in the system, right? This nitrate, if the concentration of nitrate exceeds 45 milligram per liter, if the concentration of nitrate exceeds 45 milligram per liter, and if such water is consumed by the infants or the newly born babies, it leads to a disease which is termed as blue baby disease. Blue baby disease, which is known as methyboglobimania. So this is the disease caused by the excess nitrate present in your water, and if such water is consumed by any of the infants, it causes a disease which is known as blue baby disease and also known as methyboglobimania, right? So these are all the chemical water quality parameters that are there. Next is the biological water quality parameter. So when we talk about biological water quality parameter, I am talking about calculating the quantity of pathogens. And pathogens are disease causing microorganisms. These are disease causing These are disease-causing microorganisms, right? These are disease-causing microorganisms. These pathogens are very tedious to measure. To measure these colonies of pathogens is a kind of very costly and a tedious affair. So what we do is, we measure the colonies of coliforms. We measure the colonies of coliforms. We measure the colonies of coliforms, in which we measure E. coli. We measure the colonies of coliforms, that is E. coli, and these colonies, these coliforms are non-disease causing microorganisms, and these coliforms can be easily measured. So what we want to measure? We want to measure the colonies of pathogens, but actually we measure the colonies of coliforms and we calibrate the colonies of coliforms with the colonies of pathogens present in the medium. So what we want is, we want to measure the colonies of pathogens, but we measure the colonies of coliforms and we calibrate back to the colonies of pathogens. So these can be measured using a sterile membrane technique. So the first technique that is used to measure these pathogens is known as a sterile membrane technique. A sterile membrane technique. And in sterile membrane technique, what we do is, we have this water sample, and this water sample contains both pathogens and coliforms. This water sample contains both pathogens and coliforms like this, right? This water sample has both. We pass this water sample through the sterile membrane. We pass this water sample through the sterile membrane. We pass this water sample through this sterile membrane, right? So over this sterile membrane, all the pathogens and the coliforms will be restricted. All the pathogens and coliforms will be restricted, and we get a water free from all the microorganisms, right? Now we place this sterile membrane in an incubator. We place this sterile membrane in an incubator at 35 degrees Celsius. Temperature is 35 degrees Celsius and duration is 48 hours. Duration is 48 hours, right? We keep this sterile membrane inside this incubator, and this sterile membrane contains both. It contains both. It contains coliforms as well as contains pathogens, right? So here we have kept this, and over this sterile membrane we add M endomedium. We add M endomedium, and this M endomedium, this is M endomedium, and this M endomedium is a food for coliforms. This is the food for coliforms, right? This is the food for coliforms. So we have given food for the coliforms, but the food for pathogens is not available in the system, due to which these pathogens start undergoing endogenous respiration. And due to this endogenous respiration, they start killing themselves, right? They start eating themselves. So through this endogenous respiration, these microorganisms, or especially these pathogens, they start eating themselves, due to which after 48 hours, what happens is, in this over this sterile membrane, only coliforms will be present. So after 48 hours, when we take out this sterile membrane, we calibrate the colonies of coliforms after the incubation period with the colonies of pathogens that are originally present in the water sample. Okay, so what we do? we calibrate colonies of pathogens, we calibrate colonies of coliforms after incubation with the colonies of pathogens before incubation. With the colonies of pathogens before incubation, right? So this is how we calibrate the colonies of coliforms with the colonies of pathogens. So hopefully you have understood this, how the calibration is done. The next test that we do to get the concentration is MPN test. It is MPN test. So this duration of incubation for this is 20 hours. This is not 48 hours. This is 20 hours. This T is 20 hours. This T is 20 hours, right? Next is the next method through which we get the colonies of pathogens is MPN test. MPN test. And MPN test is the most probable number test in which we prepare 3 dilutions. We prepare 3 dilutions, and for every dilution, we prepare 5 duplicates. For every dilution, we prepare 5 duplicates. For every dilution, we prepare 5 duplicates. So 3 dilutions we have like this. So this is one dilution. This is my dilution number 1. This is my dilution number 2. And this is my dilution number 3. Right. So in the first dilution, I have 10 ml of the sample. For first dilution, I have 10 ml of the sample. In the second dilution, I have 1 ml of the sample, and remaining 9 ml is filled with the aerated water. And in the third dilution, I have 0.1 ml of the sample, and remaining 9.9 ml is filled with the aerated water. So likewise, we will have 3 dilutions, and for every dilution, I have 5 duplicates, right? Now what I will do, I'll add lactose broth. To all these 15 test tubes. I'll add lactose broth to all these 15 test tubes. Again, this lactose broth is the food for coliforms. It is the food for coliforms. Right? And after adding lactose broth, I am going to seal the top of all these test tubes, right? I'll just seal the top of all these 15 test tubes like this by using cotton. I'll seal the top of all these 15 test tubes using cotton. So once after adding the lactose broth, I have sealed the top of these 15 test tubes using cotton. I have restricted the entry of oxygen inside these test tubes. So whatever decomposition that will be happening in the anaerobic condition, okay? Now these test tubes, all these 15 test tubes are placed in an incubator. All these 15 test tubes are placed, inside incubator. They are placed inside incubator at 35 degrees Celsius, and for 48 hours. At 35 degrees Celsius for 48 hours. So what will happen in these 48 hours is, all the coliforms will grow because coliforms have food lactose broth, but these pathogens, they are lagging in food. They having less amount of food, or they are having scarcity of food, right? So in this type of situation, these pathogens will undergo endogenous respiration, and they will going to have the anaerobic decomposition for themselves. The end product of anaerobic decomposition is the acids, alcohols and gases. right? So after this days of incubation, after 48 hours of incubation period, we will going to take out these test tubes and we will going to open the lid of these test tubes, right? So this is my test tube. I'll open the lid of my test tube, and what I'll do is I'll bring one matchstick close to the mouth of this test tube. If I hear a popping sound, if I hear a popping sound, it means that gases are formed. It means that gases are formed, and it means that my pathogens are decomposed anaerobically. Okay. So I will check in how many test tubes these gases are formed. So the number of tubes in which these gases are formed are termed as positive tubes. The number of tubes in which these gases are formed are termed as positive tubes, right? Or are termed as positive tubes. So what I will do, out of 5 test tubes for every dilution, out of 5 test tubes for every dilution, how many tubes are showing the positive result or the formation of gases, that I will note down. I will note down the number of test tubes that are showing positive result, that is the formation of gases in them, right? So basically what I will have, I'll have the dilution, that is 10 ml, 1 ml and 0.1 ml, right? I'll have dilution like this. After that, I will going to have the number of positive test tubes. Out of 5, how many test tubes are showing positive results? So say 4, 4 and 3. So these are the number of positive tubes. These are the number of positive tubes. Positive tubes that are showing the formation of gases, right? So I have to just record this. After this, what I have to do is, I have to take the MPN chart. I have to take the MPN chart. This MPN chart is already prepared. I have to take the MPN chart, and corresponding to this MPN chart, in this MPN chart, you will be given with the dilutions. So 10 ml, 1 ml and 0.1 ml. Like this, dilutions will be given, and in the last column you will be having MPN value per 100 ml, right? Per 100 ml. So likewise, you will going to have 4 columns for this MPN chart like this, right? This you have 4 columns like this. So we have all the permutation and combinations of these positive results. Like for example, if you get all the 5 tubes to be positive, you have x1 value of MPN. If you have something like 5, 4, 4, you have x2 value of MPN. If you have this combination of 4, 4, 3, you will have some x3 value of this MPN. So you have to directly report this x3 value of MPN corresponding to these number of positive tubes. So you have to perform the experiment, and after you are performing the experiment, when you get the number of positive tubes, you have to just compare it with the MPN chart to get the value of MPN directly, right? If the dilutions that you have performed in the lab and the dilutions of the MPN chart does not match, right? For example, if you have made the dilutions like this, for example, if you have made the dilutions like this, 100 ml, 10 ml and 1 ml. If you have made the dilutions like this and you have the MPN chart corresponding to 10 ml, 1 ml and 0.1 ml, then how to report the final answer? In this case, your final MPN value that you will report is equal to x3 is equals to x3, this MPN value from the chart. First you have to match the number of positive tubes with the combination in the MPN chart, and you have to take this x3 value multiplied by the first dilution of MPN chart, multiplied by the first dilution of MPN chart divided by the first dilution of test performed. First dilution of test performed, right? First dilution of test performed. So for here, how we will report MPN? So for this question, MPN can be reported as MPN is equals to x3 multiplied by the first dilution of the MPN chart, that is 10 ml. So first dilution of the ambient chart is 10 ml divided by the first dilution of the test performed, that is 100 ml, right? So X3 multiplied by 10 and divided by 100. So here you will report the ambient value as X3 by 10. So this is how you need to report the ambient value if the dilution in the ambient chart does not matches with the dilution of the test that you have performed. Okay. So hopefully you have understood all these chemical, physical and biological water quality parameters. We will have a break of 15 minutes and then we will continue with the treatment of water. So welcome back. We have discussed all the physical, chemical and biological water quality parameters to analyze the quality of water. Once we have analyzed the quality of water, the next thing that comes in the chain is the treatment of raw water. So the next topic of discussion is treatment of raw water. Degree of treatment given to raw water, the degree of treatment, that is the amount of treatment that is given to the raw water, it depends upon the existing quality of the raw water. It depends upon the existing quality of raw water. It depends upon the existing quality of raw water and the desired quality of treated water. And the desired quality of treated water. And the desired quality of treated water, right? So the degree of treatment given to the raw water depends upon the existing quality of the water and the desired quality of the treated water. When I talk about the desired quality of the treated water, I am talking about that all the parameters, it may be physical, chemical or biological, all these parameters should have a value less than the acceptable limit. That is the desired quality of the treated water. Then only we can transfer this water or supply this water to the community for different usages, right? Now talking about the treatment of raw water, so there are different treatment techniques that are used. First one is screening. Next is aeration. Then we have sedimentation. Next we have coagulation and flocculation. Coagulation and flocculation. Next we have filtration. Next is softening. And the last one is disinfection. And last one is the disinfection. These are all the treatment techniques that we go with raw water, right? So starting with the first treatment technique, that is screening. So screening is done to remove coarse suspended solids. To remove coarse suspended solids. Screening is done to remove coarse suspended solids from the water. Screens are of two types. Screening is performed by units which are known as screens, and screens are of two types: coarse screen and fine screen. Coarse screen and second one is fine screens. Coarse screen and fine screens, right? So these coarse screen are made up of bars, hence they are also known as bar screens, right? So we use bars like this, So we have these bars which are arranged like this, and these bars will going to restrict all the coarse suspended solids over them. These bars will going to restrict coarse suspended solids over them, right? So diameter of these bars lies in the range of 10 to 15 mm. Diameter of these bars lies in the range of 10 to 15 mm, and the center to center spacing of these bars lies in the range of 20 to 100 mm. The center to center spacing of these bars lies in the range of 20 to 100 mm. Next we have fine screens. So fine screens are in the form of wire mesh. They are in the form of wire mesh like this. They are in the form of wire mesh like this. The mosquito nets that we use or that we apply over the window, that are one of the examples of fine screens, right? So fine screens are in a form of wire mesh having the center to center spacing of 10 mm. They have center to center spacing of 10 mm between them. They are in the form of wire mesh. These screens are provided in an inclined fashion. For example, if this is the depth of water that is flowing, right? If this is the depth of water that is flowing, this is the depth of water that is applied over the screens, then screens are placed in an inclined manner like this. The screens are placed in an inclined manner like this. So let me draw this. So these screens are placed like this. So these screens are placed like this, right? This is the depth of water that we have applied for these screens. Why we have applied screens like this with some angle theta? These screens are applied inclined in order to increase the effective area over the screen. In order to increase the effective area of the screen, right? For same depth of water, for this same depth of water, if we have applied screen in the vertical position, then the amount of area that will be available for the screening mechanism will be less. But on the other hand, if we apply screen in an inclined position, then now the available area for screening will be more, right? So these screens are applied in an inclined fashion. Second thing is, when the water passes through the screen, the bars of the screen will going to apply frictional force over this water which is passing through the screen. Due to the frictional force applied by this bars of the screen, the water that is passing through the screen will undergo some head loss. That head loss can be calculated as, so head loss through the screen can be calculated as K upon 2G V square minus U square. So this K by 2G is a constant. V is velocity through the screen. It is velocity through the screen. It is velocity through the screen. And U is velocity of approach. U is velocity of approach. U is velocity of approach. So V is this velocity through which the water is passing through the screen, and U is the velocity with which the water is approaching towards the screen, right? Over the period of time, when more screens will get choked or more suspended particles will clog the screen, the available space through which the water is flowing over the period of time, that will going to reduce. If the area available through which the water is passing through the screen, it will reduce, your value of V will going to increase. Your value of V will going to increase, and if V increases, it means that your head loss will also going to increase if more voids of the screens are choked. So over the period of time, the head loss through the screens will going to increase because velocity through the screen will going to increase, right? So this is all the basics about your screening mechanism. Screens are used to remove the coarse suspended solids from your raw water. Next method of treatment is aeration. In aeration, raw water or water is brought in intimate contact with the air. Water is brought in intimate contact. Water is brought in intimate contact with the air. Water is brought in intimate contact with the air, due to which what happens is from air from air to water, from air to water, oxygen transfer happens. From air to water, oxygen transfer happens. Now, addition of oxygen will going to increase the dissolved oxygen concentration, and if the dissolved oxygen concentration increases, then what aeration process removes? Please understand this. So, aeration is basically the addition of oxygen into our water sample, which increases the dissolved oxygen concentration of our water. Oxygen is a strong oxidizing agent. So first of all, aeration will going to remove all the color causing compounds. All the color causing compounds. All the color causing compounds. It will going to remove all the color causing compounds, especially iron and manganese. If color causing compounds like iron and manganese are present in your water sample, you can perform aeration in order to remove these color causing compounds. Second thing is, aeration removes all the dissolved gases. Aeration removes all the dissolved gases. Aeration removes all the dissolved gases. Aeration removes all the dissolved gases like CO2, H2S, CH4. All the dissolved gases will be removed by the means of aeration. Next is aeration. Due to aeration, oxidation of organic matter takes place. Oxidation of organic matter takes place. Oxidation of organic matter takes place, due to which this organic matter is removed from the system. And last is, due to aeration, phenols which causes taste and odor, which imparts taste and odor to your water sample, is oxidized. Phenols are oxidized and are removed from the system, right? So aeration removes the color causing compounds, aeration removes other dissolved gases, aeration also removes the organic matter that is present, and aeration removes the phenol which provides taste and odor to your water sample, right? But the only drawback with aeration is it increases the acidity of water. It increases the acidity of water. It increases the acidity of water, right? It increases the acidity of water. So these are the key points in aeration. Thank you so much. Thank you so much, Vijay sir. Thank you so much. Thank you, Amit sir. Next is, these aeration is performed using following techniques. First one is known as, these aerations are performed using following techniques. So first method by which aeration is performed is known as spray nozzle method. Spray nozzle method. Spray nozzle method. Next method by which aeration is performed is known as tray tower method. Tray tower method. Tray tower method. Next is your cascade aerator. Cascade aerator. Next is your cascade aerator. And last one is your diffused aerator. Diffused aerator, right? So all these are the techniques through which aeration is performed. Out of all these techniques, tray tower method is the most efficient method of aeration. It is the most efficient. It is the most efficient method of aeration. Cascade aerator is the least efficient method cascade aerator is the least efficient method of aeration, but cascade aerator does not have any operation and maintenance cost. Hence, cascade aerators are provided cascade aerators are provided for treating water, right? For treating community water, we provide cascade aerator because it does not have any operation and maintenance cost. For spray nozzle method and diffused aerator, extra amount of money is required or extra fund is required for generating this pressure in the spray nozzle method and the diffused aerator. Hence, these two methods are avoided. Okay. So, this is all the briefing about aeration. Next method of treatment is sedimentation. So, the settling of particle in the sedimentation tank, depends upon a single parameter which is known as the specific gravity, right? So, settling of particle depends upon a single parameter which is known as the specific gravity of a particle. If the specific gravity of the particle is more, it will going to settle more easily, right? And how we define specific gravity? Specific gravity can be defined as the ratio of their unit weight, the ratio of the unit weight of the solid with the unit weight of water, or it can be calculated as density of solid divided by the density of water, or this specific gravity can be calculated as weight of solids divided by the weight of standard fluid of same volume right? So, this is how you can calculate the value of specific gravity. For us, the standard fluid is water. So, we take the weight of water having the same volume as that of solids. So, that is how we can calculate the specific gravity. A specific gravity is a single parameter which decides how the particle will settle. If a particle has more specific gravity, it will going to settle easily. You can just see these values for inorganic solids. The value of G lies in the range of 2.6 to 2.9. This is the range of value of G for inorganic solids, and for organic solids, the value of G lies in the range of 1 to 2, right? So, as you can see here, for organic solids having less value of specific gravity will going to settle in more duration of time as compared to the inorganic solids, okay? Now, when we talk about the settling of the particle, the settling of the particle is also characterized by one more parameter which is known as the settling velocity. This settling velocity of the particle is determined using Stokes' law. And according to Stokes' law, settling velocity Vs is equals to under root 4 by 3 Gd into G minus 1 divided by Cd. This is the expression for calculating the settling velocity of the particle for general condition, right? Where Cd is the coefficient of drag, G is the acceleration due to gravity, D is the size of the particle, and G is the specific gravity of the particle, right? Next, if we have a laminar flow condition, for laminar flow condition, that is, size of the particle is less than 0.1 mm and Reynolds number is also less than 1. For this flow condition, your settling velocity can be calculated as Vs is equals to 1 upon 18 gamma W d square into g minus 1 divided by mu, right? So using this relation is only applicable for laminar flow condition. Only for laminar flow condition you can use this expression. For laminar flow condition, the value of CD is 24 by RE. It is 24 or 34 by RE. Okay, we'll just leave this. So you can calculate your settling velocity using this expression, right? But sometimes in the question, instead of this dynamic viscosity, coefficient of dynamic viscosity, instead of coefficient of dynamic viscosity, we are given with the coefficient of kinematic viscosity. We are given with the coefficient of kinematic viscosity. So this is nu, which is the coefficient of kinematic viscosity, which is the coefficient of kinematic viscosity, right? So how to convert this? We have one simple relation. Nu is equals to mu by rho W, right? So whatever fluid you are using divided by the density of that fluid. For us, the fluid is water. That's why we are using gamma W and rho W. Now, how to use this in this formula? So you can write gamma W is equals to, so you can write Vs is equals to 1 upon 18. This gamma W can be written as rho W into G. It is written as rho W into G into D square into G minus 1 divided by mu, right? Now this mu and rho W will be equal to nu. So you can just replace this expression and write Vs is equals to 1 upon 18 G d square into G minus 1 divided by nu, right? So this is the expression for settling velocity if you are given with the kinematic viscosity of water. Is this okay? I guess this is clear to you. So this is how you can calculate the settling velocity of the particle, right? Now moving on with this. Sedimentation is carried out in units. Sedimentation is carried out in units which are known as settling tanks. And these settling tanks are of two types. First type of settling tank is known as fill and draw type sedimentation tank or settling tank. Fill and draw type sedimentation tank. In this type of sedimentation tank, we just fill the water for 24 hours, and in this 24 hours, the suspended solids settle under their own weight. And after 24 hours, whatever water that has settled, we take out, right? For fill and draw type settling tank or sedimentation tank, your detention time, that is the time for which water is present inside the tank, is 24 hours. And if you are providing mechanical, if cleaning is done mechanically, for mechanical cleaning, if cleaning is done mechanically, then sludge zone is not provided. So if cleaning is done mechanically, then sludge zone will not be provided. Detention time is 24 hours, right? Volume of the tank can be calculated as discharge multiplied by the detention time. Discharge multiplied by the detention time. This is how you can calculate the volume of the tank, right? So this is all about first type of settling tank or sedimentation tank, which is termed as fill and draw type sedimentation tank, in which the water is filled for 24 hours, and in this 24 hours, the settling of the particle will happen, and after that, we draw this water, right? And if the cleaning is done mechanically, then sludge zone is not provided for these type of settling tanks. Moving on. Next type of sedimentation tank is continuous flow type. Continuous flow type sedimentation tank, right? Now, in the continuous flow type sedimentation tank, as the name says, continuous flow is maintained. Depending upon the direction in which the flow is maintained, it is further classified as horizontal flow type tank and the vertical flow type tank. If the flow is maintained in the horizontal direction, it is termed as the horizontal flow type sedimentation tank. So, this continuous flow type tank is further classified as horizontal flow type sedimentation tank, horizontal flow type sedimentation tank, or vertical flow type sedimentation tank, or vertical flow type sedimentation tank. Now, these continuous flow type tanks are designed for the removal of concerned size of the particle, right? So, for this concerned size of the particle, the settling velocity of this concerned size of the particle is termed as surface overflow rate. So, I'll just write down everything. For horizontal flow type tank, in these tanks, the flow is maintained in the horizontal direction, and for the vertical flow type tank, the flow is maintained in the vertical direction. All these tanks, all the continuous flow type tanks are designed for the removal of concerned size of the particle, right? So, for horizontal flow type tank, all the particles, I'll write this, particle of size greater than and equal to concerned size of the particle, concerned size of the particle will be 100% removed, and also particles which are having the size less than the concerned size of the particle, they are partially removed, right? So, particles with lesser size, particles with lesser size are partially removed, right? Are partially removed. Particles of size lesser than the size of the concerned size of the particle are partially removed. But for vertical flow type tank, only particles of size greater than or equal to concerned size of the particle, greater than or equal to concerned size of the particle, are 100% removed, Particles of size less than the concerned size of the particle will not be removed in the vertical flow type tank. So, as you can compare these two, obviously for horizontal flow type tank, more amount of particles are removed because we are also getting some partial removal of particles of size less than the concerned size of the particle. But that partial removal is not happening for this vertical flow type tank. So, if I'll write efficiency for horizontal flow type tank, is more than the vertical flow type tank, vertical flow type tank, right? So the efficiency for horizontal flow type tank is more than the efficiency for vertical flow type tank. And why we are getting more efficiency for horizontal flow type tank? Because we are getting the partial removal of particles of lesser sizes also, right? In order to calculate the efficiency of sedimentation, so efficiency of, first of all, percentage removal of a smaller size of particle, percentage removal of smaller size of particle, percentage removal of a smaller size of particle can be calculated by taking the ratio of small h to capital H into 100, where capital H is the depth of water in the tank and small h is the height up till which the complete removal of this smaller size of particle is possible, right? We can also calculate this by taking the ratio of their settling velocity. So Vs1 is the settling velocity of smaller size of particle divided by the Vs, which is the settling velocity of the concerned size of the particle. And the settling velocity of the concerned size of the particle, this settling velocity of the concerned size of the particle is also known as surface overflow rate. It is also known as surface overflow rate. It is also known as surface overflow rate, right? So this Vs is known as the surface overflow rate. So Vs1 divided by Vs into 100. Or if the flow is laminar, only during laminar condition, we can also get this percentage removal as d1 square divided by d into 100, where d1 is the size of the particle lesser than the concerned size. D is the concerned size of the particle multiplied by 100. So d1 square divided by d square, and this formula is only applicable for laminar flow condition. Only for laminar flow condition you can take this ratio. Only for laminar flow condition you can take this ratio of d1 square divided by d square into 100. So the percentage removal of smaller size of particle can be calculated by any of these formulas. Now talking about the efficiency of sedimentation. So efficiency of sedimentation, your efficiency of sedimentation is equals to percentage removal multiplied by the percentage concentration. So this efficiency of sedimentation can be calculated using percentage removal multiplied by percentage concentration. So if axis is the percentage finer with respect to concerned size of the particle, d, and d is the concerned size of the particle. D is the concerned size of the particle. Then the percentage can be calculated as percentage efficiency of sedimentation can be calculated as 100 minus excess. So all these particles which are having size more than the concerned size of the particle, all these particles will be 100% removed. So multiplied by 1 plus summation of I is equals to 1 to n USI divided by Vs into 100. Vs multiply by delta Xi into 100, right? So if you have a continuous curve, you can divide the percentage concentration into small strips, and for that percentage concentration of particles, you can have the average velocity USI bar. You can have the average velocity for those percentage concentration delta Xi, and then divided by Vs, which is the concerned size of the particle. So using this relation, you can easily calculate the efficiency of sedimentation. Is this okay? I guess this is okay. Now talking about the horizontal flow type tank. So this all we have discussed about the horizontal flow type tank. For horizontal flow type tank, flow type tank for horizontal flow type tank, right? Your detention time TD, it is equal to length of the tank divided by velocity of flow VF. It is also equal to the depth of water divided by the settling velocity Vs. And this settling velocity is the settling velocity of the concerned size of the particle, which is also known as surface overflow rate. This is also known as surface overflow rate. This is also known as surface overflow rate. Then plan area can be calculated as design discharge divided by the surface overflow rate. Design discharge multiplied by the surface overflow rate. Your volume of the tank, V is the volume of the tank, it is calculated as design discharge multiplied by the detention time. So using these relations, you can calculate all the entities that are required with respect to the sedimentation basin. It can be any sedimentation basin, right? So using all these relations, you can easily calculate the quantities which are required. Is this okay? So hopefully you have read till this point and you have learnt a lot regarding environmental engineering. So for now, that is all from my side, and I wish you all the best for the upcoming GATE examination. Thank you so much.